NASA saw it first, and then went silent. A comet, 3 Atlas, moving in ways no physics textbook can explain. Its data vanished from public records just days before the agency shut down. Why? What did they find out there? And why are scientists suddenly afraid to talk about it? Hello there, and welcome to the Sleepy Astronomer, a quiet space where the universe speaks softly, and even its biggest mysteries are told like bedtime stories. If these calm explorations of space and wonder help you drift deeper into thought, subscribing to the Sleepy Astronomer helps this little world of curiosity grow, so more dreamers can listen to the stars and rest beneath their light. Tonight, we turn toward 3I Atlas, an interstellar traveler NASA studied, then quietly removed from discussion. What could a single comet reveal that made scientists hesitate to speak? Was it just another piece of cosmic ice, or something that challenges everything we thought we knew about the solar system? Breathe slowly, because by the end of this story you'll understand why 3I Atlas has left even the brightest astronomers speechless. This is the Sleepy Astronomer. It begins with stillness, a quiet night like thousands before it, the kind of night where the world exhales, when even the noise of thought seems to slow. You stand beneath the open dark, the air cool against your skin, the stars above infinite and precise. They seem eternal in their positions, each point of light fixed, patient, unchanging. Yet tonight, something feels slightly off. Not wrong, just different, as if a thread of the universe has trembled for the briefest moment. You can't see it with your eyes, not yet. But somewhere deep inside, the rhythm of the cosmos shifts. It's the kind of change that only sensitive instruments or sensitive souls can sense, a tremor of motion where there should be calm. Above you, telescopes keep their endless vigil, drinking light from the edge of space. In their silent machinery, a story is beginning to form, one not made of words, but of faint reflections, flickers, and coordinates. You imagine the observatories scattered across the Earth, domes gleaming under starlight, each one a listening ear to the universe. Somewhere in Hawaii, a mirror catches a signal, a faint smudge that moves just slightly faster than a comet should. Somewhere in Chile, a researcher blinks at the monitor, recalibrating for what might be an error. And yet the motion persists, not random, not explainable, just a quiet difference that refuses to fade. You feel it, even from here, a kind of cosmic heartbeat, slow but sure. Astronomy, after all, begins with noticing, with patience, with wondering why. Every movement of the heavens tells a story, the slow turning of planets, the distant shimmer of galaxies, the drift of ice and dust across the void. But this story is different. This object, unnamed, unclassified, unseen by most eyes, doesn't move like the others. It doesn't circle the sun in loyal orbit. It passes through, like a thought that belongs elsewhere. In the observatory logs, someone writes the first line of its presence: unidentified object detected. Unusual velocity numbers follow, coordinates, distances, magnitudes, and with each line the pattern grows stranger. It's coming from beyond Neptune, slipping into the solar system on a path no planet could command. You picture the scientist leaning forward, the glow of the monitor washing pale light across their face. The night outside is silent, the dome slowly rotating to keep up with the stars. For a moment, human curiosity and cosmic motion align, two forms of awareness meeting across vast space. They don't know it yet, but this will be named 3I/ATLAS, the third known interstellar object to visit our solar system, a traveler from another star, a wanderer between suns, a messenger of distances so immense that light itself takes generations to cross them. But before names, before theories, before press releases, there is only the act of noticing, of seeing something that should not be there and choosing to pay attention. You breathe slowly, feeling the vastness press gently around you. The night sky, you realize, isn't silent at all. It hums, a deep, low harmony of motion and light. Every star, every dust grain, every unseen particle moves in rhythm. To notice even a slight deviation is to hear a faint discord in an endless song. You imagine what it must feel like to discover such a thing, the mix of wonder and disbelief. The quiet thrill of realizing that the universe is not finished surprising you. Somewhere a group of astronomers begins comparing notes. They double-check the data, they verify the source. Could it be an asteroid, a comet, a satellite gone astray? Each hypothesis collapses under the same weight. It doesn't behave like anything we know. And yet it is there. The signal repeats. The coordinates shift exactly as predicted by orbital models, except those models assume the sun has hold over it. But it doesn't. This object is merely passing through, free from the sun's pull. You let that sink in, the idea of something unbound, something wandering the darkness between stars, untouched by gravity's demand. It has travelled perhaps millions of years through interstellar night, carrying within it the dust and memory of another system entirely. And now, by chance, it brushes ours, a brief hello in the cosmic dark. Astronomy has a quiet poetry of its own. Each discovery is a love letter written to the unknown. The telescopes listen, the data whispers, and human hands translate light into meaning. This one, though, this one feels different. The brightness fluctuates in a rhythm that feels almost alive. Its tail blooms with fragments not seen in any previous visitor. You think of comets as the universe's archivists, frozen memories of formation, wandering time capsules of what once was. To find one from another star is to glimpse a story written in a language we can barely read. The night deepens, the stars remain patient. Somewhere in the distance, servers record streams of numbers, bits of light turned into lines of code, each digit an echo from another world. You imagine them stacking in silent order, like snow falling in an unseen place. The data grows, the mystery expands, and as you stand beneath it all, you feel something shift within you too. The boundary between observer and observed blurs. You're no longer just watching the sky, you're part of its noticing, part of the long chain of curiosity stretching from ancient stargazers to modern scientists. Somewhere above, the object continues its path, silent and swift. It doesn't know it has been seen. It doesn't care for names or recognition. It simply moves, obeying the physics written into the universe itself. And yet, because you have noticed it, it now exists differently, not just as rock and ice, but as meaning. The night ends slowly. Dawn begins to pull faint light along the horizon, but your thoughts remain suspended in the dark. You wonder how many others have passed unseen, slipping through history without witness. You realize that for every discovery made, 1,000 have gone unnoticed, and maybe that's what makes this one matter so much. Somewhere, in a quiet control room, a message pings across an internal NASA network. Possible interstellar object. Please confirm trajectory. The world doesn't know it yet, but a new story has begun, a story not of what's known, but of what refuses to fit neatly into knowing. And as the sky brightens, you look up one last time feeling the faint tug of something vast and wordless. Because sometimes, all discovery asks of you is to notice. And somewhere, even now, that visitor continues its journey, waiting for someone else to realize what it means to come from beyond the sun. In that quiet distance, something ancient keeps moving, and you begin to wonder where it came from, and what secrets it might carry from a past that is not ours. The first thing astronomers confirm is the orbit, and that's what changes everything. The new object's path doesn't loop back toward the sun, nor does it curve as most comets do. Instead, its trajectory forms an open line, a hyperbola. In simple terms, it means the object is not bound by the sun's gravity. It came from far beyond our solar system, and it will never return once it leaves. That fact alone makes it extraordinary. The observatory teams around the world begin to share their data. Coordinates from Hawaii, Chile, and Arizona start matching up. The numbers reveal a steady movement. The object entered from the direction of the constellation Lynx, moving faster than anything formed here should move, nearly 60 kilometers per second relative to the sun. That speed is too high for any known comet or asteroid from our solar system. Gravity can bend it, but not capture it. When scientists calculate its orbit, the eccentricity, the measure of how stretched its path is, comes out greater than 1. That single number is the clue. It's not a local body. It's interstellar. It came from outside the sun's domain. At first, no one can quite believe it. A few years earlier, another interstellar object had been found, 1I/Oumuamua, but that discovery was still debated and uncertain in many ways. Could another one already be here? The odds seem tiny, yet the data is clear. The equations don't lie. The shape of its orbit, the angle of its entry, the speed of its exit, all confirm the same conclusion. This new traveller is labelled 3I/ATLAS, the third interstellar object ever recorded. The 3I stands for Third Interstellar, while ATLAS refers to the telescope survey system that detected it. The name feels formal, but what it represents is something almost unbelievable. A piece of another star system passing through ours. You think about how space is mostly empty, vast regions of nothing between stars, and how rare it must be for an object like this to cross our neighbourhood. Yet here it is, cutting through the solar plane at a steep angle, moving so fast that no planet, no orbit could claim it. It's a visitor without a past we can trace. Researchers begin to model its origin. By simulating its backward trajectory, they try to guess which star system it might have come from, but the more they calculate, the less certain it becomes. Interstellar space is full of gravitational influences, faint tugs from stars, invisible pushes from gas clouds. Over millions of years, such tiny forces can alter a course so completely that no one can tell where it began. It's like trying to follow a single ripple backward through an ocean. By the time it reaches you, every direction looks possible. The idea unsettles many scientists. Normally, comets tell a story. Their orbits link them to the Kuiper belt, the Oort cloud, or some family of objects formed long ago. But this one tells no such story. It doesn't fit any model of local formation. It carries no label of belonging. And yet, its very existence offers proof of something beautiful. That other solar systems eject material just as ours does. Stars are not isolated. They share pieces of themselves through the motion of their debris. Over billions of years, these fragments travel across the galaxy, drifting until they cross paths with another system. For a brief moment, a geological instant, two distant origins touch. You imagine the place it came from. Maybe it was born near a red dwarf star orbiting a world of frozen oceans. Maybe it was thrown out during the violent birth of a planet. Or maybe it drifted through interstellar space for so long that its home star no longer exists. Whatever the truth, its journey has been one of silence. Centuries and centuries of motion through cold vacuum, no light, no warmth, only inertia. The scientists analyze its light. Spectrometers separate it into wavelengths, revealing a mix of materials. It reflects sunlight poorly, meaning its surface is covered in dark dust, probably mixed with volatile ice. Some readings show traces of cyanide and carbon compounds, common ingredients in comets, but still interesting. If these molecules were formed around another star, they might carry information about chemistry beyond our system. The more data comes in, the more 3I/ATLAS looks like a comet. It has a faint tail, a coma of vapour around its nucleus, and it brightens slightly as it approaches the sun, but its speed, its orbit, its timing, all show the same thing. This is not one of ours. Astronomers start asking deeper questions. How many interstellar visitors pass through undetected? How many sweep by unseen, too faint for our instruments? Space is large, and even 1 million such travellers could cross without ever meeting a telescope's gaze. The discovery suggests that interstellar comets might be common. We just haven't been looking long enough to find them. There's also the emotional weight of it, to realise that a piece of another solar system is now visible in our skies. For most people, the stars are unreachable, fixed points of light. But here, suddenly, is something that came from there. It's not a beam of light. It's matter, real and solid, drifting close enough for us to study. It makes the galaxy feel smaller and more connected. In laboratories and offices, the data continues to flow. Teams calculate dust release rates, spin patterns, possible fragmentations. Others debate its exact classification. Is it truly a comet or an asteroid with a thin volatile layer? There's no final answer yet. The line between those two categories blurs more with every observation. For you, though, the fascination lies not in the classification, but in what it represents. Proof that the universe exchanges pieces of itself. Every solar system contributes to the collective story of the galaxy. Some fragments wander for ages, untouched, until a new star's gravity bends their path for a moment. That's what's happening now, and yet, amid the excitement, there's also a quiet sadness. 3I/A TLAS won't stay long. Its path is steep and swift. Soon it will pass beyond Jupiter's orbit, then the outer edges of the solar system, and return to the endless dark. It will never circle back, never be captured. Once it's gone, only the data will remain, a few terabytes of numbers, a trail of light across our sky. For all its speed and mystery, it is still a piece of natural motion, another product of gravity's ancient game. It doesn't carry messages or intention, only the physics of momentum and ice. And yet, that is enough. The universe doesn't need meaning to be profound, it only needs motion. As the data settles, as telescopes record their final measurements, scientists begin preparing reports and simulations. They will trace its orbit, publish the findings, and share the story of another interstellar visitor. But one question remains unanswered, and it lingers at the edge of every discussion. If this object can arrive from so far away, how many others are still out there, crossing smartly between stars, unnoticed, unrecorded, passing through the darkness with no one watching? And as 3I/TLAS continues its brief visit, the question grows louder in your mind: what secrets lie in the comets that never stay long enough to tell their story? You sit before the faint glow of the observation monitor. The graphs are steady at first, then they rise and fall with a rhythm that doesn't match anything familiar. The readings belong to the same moving dot that astronomers had first identified weeks ago. The object now officially named 3I/ATLAS. But tonight, the numbers are not behaving. The spectral lines, those color-coded fingerprints of light, are out of place. In every known comet, sunlight warms the surface and releases predictable gases: water vapor, carbon dioxide, ammonia. These gases scatter light in patterns that can be measured and catalogued. But the spectrum of 3I/ATLAS tells a different story. Its light carries traces of compounds that should not exist this close to the sun. It seems to be shedding materials that belong to far colder regions of space, the kind found beyond the outermost planets, perhaps even beyond our solar system's boundary. You look closer at the chemical traces. There are hints of carbon monoxide and molecular nitrogen in quantities far above normal. These are fragile ices, the kind that evaporate almost instantly under sunlight. Yet here they are, still intact, still glowing, still escaping from the comet's surface as if protected by some invisible shield. You realize this means only one thing. This object formed in a place so cold and distant that sunlight had never touched it until now. 3I/TLAS, then, is not just a visitor. It is an immigrant from another star system. That realization spreads slowly, like warmth in your chest. You think about the vast distances it must have crossed. In our galaxy, stars are separated by light years, immense gulfs of emptiness. For something to travel from one system to another, it must survive cosmic radiation, gravitational pulls, and collisions with invisible debris. Most interstellar objects, if they exist, never make it through. Yet here one is, passing before our eyes. Scientists start to question its structure. Could it even be called a comet? The traditional definition, a small icy body that forms tails of gas and dust when heated by the sun, does not quite fit. The tail of 3I/TLAS forms unevenly, as if the material is not evaporating smoothly but bursting in intermittent waves. Images from ground-based telescopes show it brightening unexpectedly, then dimming again without reason. A typical comet brightens steadily as it nears the sun, following a simple curve that astronomers can predict. 3I/TLAS ignores that curve. It brightens too early, fades too soon, then flares again, as if something deep within it is reacting to exposure, perhaps cracking, perhaps awakening. You imagine the interior of the object, layers of frozen material pressed together over millions of years, holding ancient chemistry from another world. Somewhere inside, volatile gases might be trapped under crusts of dust. When sunlight finally reaches them, they burst through the surface, creating sudden plumes that change the comet's brightness and direction. But even that does not explain everything. Its rotation appears irregular, not spinning like a top, but wobbling, precessing, tilting. The data suggests it could be tumbling chaotically, perhaps due to uneven jets of gas escaping at random angles. This behavior is known in cometary physics, but the degree of instability in 3I/ATLAS is extreme. You think of it as a frozen traveller, spinning through the void after a long exile, now losing its balance as it approaches the warmth of another sun. When scientists model its motion, the equations keep breaking. The orbital path can be calculated backward, tracing where it came from, and it leads beyond the Oort cloud, beyond even the sun's gravitational influence. It comes from interstellar space, moving too fast to ever be captured by our solar gravity. That means it will not stay. 3I/ATLAS is a temporary visitor, destined to pass through and vanish forever. The first interstellar object ever recorded was Oumuamua in 2017, a strange, elongated body that reflected sunlight oddly and sparked debates about whether it was comet, asteroid, or something else entirely. 3I/ATLAS is the third such object observed, but unlike Oumuamua, it has a visible coma, the fuzzy envelope of gas that makes it unmistakably comet-like. Still, its chemistry and brightness patterns set it apart from anything previously known. The scientific community splits into two camps. One group sees 3I/ATLAS as a gift, a sample of another star's planetary leftovers, giving us a glimpse into how worlds form elsewhere. The other group sees something unsettling, an object that doesn't fit established theories, raising questions our models can't answer. For them, its existence is a problem to be explained away, not a mystery to embrace. You find yourself somewhere in between. The data fascinates you, but it also unsettles you. If 3I/ATLAS carries materials that defy our expectations, what else in the universe might we be misunderstanding? How many of our definitions, of comets, of origins, of belonging, depend only on what we have seen so far? A new report arrives from an observatory in Chile. The team has detected complex organic molecules, carbon chains that form the basic ingredients of life. Not living matter, but precursors. Simple alcohols, hydrocarbons, maybe amino acid fragments. These molecules are fragile and easily destroyed by radiation, yet here they are, preserved in ice older than our planet. The implication is enormous. If such chemistry exists in interstellar comets, then the seeds of life are not confined to one solar system. They drift silently from star to star. You look at the sky that evening and imagine countless other comets like this one, some falling into distant suns, some wandering eternally. Each could be carrying traces of chemistry from worlds that no longer exist. 3I/ATLAS might be a messenger, not from a civilization, but from creation itself, carrying the building blocks of everything that ever learned to think, to wonder, to look back at the stars. NASA's official reports remain cautious. They note the anomalies but avoid speculation. The language is measured, professional, detached. Unusual outgassing, non-gravitational acceleration, uncharacteristic spectral signature. Yet between the lines you sense hesitation, the quiet awareness that this discovery doesn't fit comfortably within known frameworks. Some scientists begin to suggest the possibility of contamination. Perhaps the instruments misread something, or sunlight interfered with sensors. But others point out that independent observatories using different equipment report the same results. The data is consistent across hemispheres and nights. The mystery deepens. In a closed forum, you read messages from researchers sharing early drafts and raw observations. Some of them sound excited, others uneasy. One comment stays with you. If these ratios are real, this comet was never meant to exist in a system like ours. That phrase, never meant to exist, echoes in your mind. You realize it doesn't just describe the object, but our reaction to it. 3I/ATLAS challenges comfort. It demands that we accept a universe still capable of surprising us. You close your notes and glance again at the monitor. The object continues on its path, leaving behind a thin, shifting trail of dust. Its light grows dimmer each night, but the data remains vivid, columns of numbers, each holding a fragment of an impossible truth. Somewhere deep inside that fading light are clues to how worlds form, how chemistry survives, and how chance writes the history of the cosmos. You wonder if the next readings will finally explain it, or only make the mystery deeper. The next scheduled transmission from NASA's servers is due in the morning. You mark the time in your logbook, unaware that soon those servers will go silent. And with that silence, another mystery will begin to form. You wake to an inbox that feels too quiet. The usual automated notifications, daily reports from observatories, image updates from data servers, summaries from telescope arrays are missing. The emails that once arrived like clockwork have stopped. The message logs show failed attempts to connect to NASA's main archive server. You refresh the screen twice, then again, but the result doesn't change. A line of text sits where the data should be. Service temporarily unavailable, maintenance in progress. At first, you assume it's routine. NASA's networks undergo periodic updates. Systems need calibration. But hours pass and nothing returns online. The observatory message boards begin to fill with quiet confusion. Someone posts that the Near-Earth Object Data Center is unreachable. Another reports that the Planetary Data System, which holds cometary research files, is also offline. By noon, several related databases display the same message. Then the official announcement appears. Due to the federal government shutdown, NASA is suspending most operations until further notice. You sit back in your chair, reading the sentence again. The timing feels almost unreal. Just days ago, data from 3I/ATLAS was flooding in. Now, as if on cue, everything has gone silent. The cause, technically, is political. A lapse in government funding leading to an administrative halt across federal agencies. But in effect, it means the world's most advanced scientific instruments have gone blind. Satellites still orbit, telescopes still gather light, but no one is authorized to analyze or transmit that data. Thousands of researchers are placed on unpaid leave. Laboratories lock their doors. Projects pause mid-measurement. You imagine the observatories now. Dark halls, screens powered down, rooms filled with the quiet hum of machines waiting for someone to return. Years of data collection frozen in place. Research that once connected scientists across continents suddenly feels fragile, as if knowledge itself depends on a paycheck. Outside NASA, smaller observatories and universities continue to monitor 3I/ATLAS, but their access to centralized databases is limited. Without the main network, they can't cross-reference readings or compare spectra. Collaboration falters. Even simple confirmation requests bounce back with automated replies. This account is temporarily inactive. In online forums, frustration grows. One astronomer writes, "The universe doesn't stop expanding because Congress can't agree." Another replies, "No, but our connection to it does." You realize that for all the sophistication of our instruments, science still relies on human infrastructure, servers, funding, coordination. Without it, even the most brilliant discoveries can slip into silence. You try contacting a NASA liaison you've worked with before. The email returns instantly. User not available during shutdown. You scroll through your contact list and see similar messages from others. Furloughed. Temporarily unavailable. Response delayed until operations resume. The collective silence feels heavier than any official announcement. In the following days, the comet continues its journey across the sky. Amateur astronomers post grainy images taken from backyard telescopes. A few foreign observatories publish limited data, but much of it lacks calibration. The professional-grade information, infrared readings, mass estimates, chemical analysis, remains locked behind government firewalls. For a time, rumors fill the gap. Some claim the data was intentionally hidden. Others insist it's just bureaucracy at work. You don't know which version is closer to the truth. What you do know is that every hour of silence costs information that may never be recovered. When telescopes lose contact with their teams, small details vanish, the kind that only humans notice. A faint signal in a data set might have pointed to a rare molecule. A slight shift in trajectory could have hinted at an unseen gravitational influence. Without constant analysis, these clues fade. The comet continues on its path, but its story begins to blur. You remember the excitement just weeks ago, when 3I/ATLAS first appeared in the data streams, the discovery that united teams across continents. It felt like a moment of global curiosity, a shared search for understanding. Now the same data feels like contraband, locked away not for secrecy, but for lack of permission. You open a cached version of the archive you downloaded days before the shutdown. Inside are spectral files, brightness curves, and logs from multiple observatories. The timestamps show the comet's light curve changing rapidly, more erratic than ever. It's as if the object is reacting to something, breaking apart, brightening unpredictably, defying models once again. You wish you could verify the trend, but without NASA's live data feed, it's impossible to know what's really happening. The comet is moving fast, its distance from Earth increasing with each day. Observations delayed now can't be recovered later. Once it leaves the sun's influence, it may never be seen again. Meanwhile, official NASA social media accounts remain silent. Only automated posts about previously scheduled events continue to appear. Comments fill with questions about launches, satellites, and especially about the mysterious interstellar comet. None receive replies. It feels strange how quickly silence becomes normal. After a few days, the stillness of your inbox stops surprising you. The hum of your computer becomes the only constant sound. You spend your evenings checking independent astronomy websites, hoping someone has new images or data, but most updates are minor. A few astrophotographers report the comet's brightness fluctuating wildly. One mentions that it may be fragmenting, a possibility you can't confirm. You start keeping a private log, documenting everything that remains accessible. Each entry ends with a question mark. There's no one left to verify your notes. Science, you realize, depends on community. Not just instruments or data, but people comparing, correcting, challenging. Without that dialogue, even accurate information begins to feel uncertain. Weeks pass, the government remains gridlocked, NASA remains offline. Slowly, public interest drifts elsewhere. News outlets move on to other stories. The comet fades from headlines, then from memory. Only a few dedicated observers keep watching, filing amateur reports into small online forums. You notice something subtle in those final independent reports, a small but consistent discrepancy in the measured trajectory. It's as if the comet's path has shifted slightly, deviating from the projection last calculated before the shutdown. The difference is tiny, almost negligible, but it's there. You save the data locally, planning to analyze it when access returns. Still, a quiet unease lingers. You can't help but wonder, if the trajectory really has changed, what caused it? Was it a natural outburst of gas or something else? You close your laptop for the night. The stars outside remain as they were, distant and indifferent. Yet somewhere among them, 3/a TLAS continues its silent path, an object that shouldn't exist, now moving unobserved through space. And deep within the walls of NASA's offline servers, the last full transmission about it sits untouched, waiting. When those systems come back online, you will learn what was captured before the silence began and what it might mean. The shutdown drags on longer than expected. Days turn into weeks, and the silence that once felt temporary begins to feel permanent. NASA's servers remain dark, official communication channels frozen in time. Most scientists return home, waiting for funding to resume, but a few people, you learn, don't stop working. Somewhere within NASA's digital structure, behind layers of automated locks and restricted logins, the data still exists. It isn't gone, just inaccessible. Terabytes of raw telescope imagery, spectroscopic readings, and telemetry logs rest in physical drives and mirrored cloud backups. Even when humans stop working, machines continue their routines. Automated systems still capture data, timestamp it, and queue it for upload. The servers may be offline to the public, but they still remember. You begin to understand something subtle about science in the digital age. Discovery doesn't vanish when people do. The universe keeps sending signals, instruments keep listening. The only missing piece is the interpreter, the human being who turns numbers into meaning. Without that, data becomes like an unread book, full of knowledge that no one has opened. One night, scrolling through astronomy forums, you find a comment thread discussing something unusual. A user with a cryptic handle claims to have accessed a mirror archive of the small body database, one of NASA's systems that catalogues objects like comets and asteroids. They mention that certain entries related to 3I/ATLAS were backed up before the shutdown and remain viewable through a secondary data mirror hosted at a university in Europe. The post receives little attention. Most users assume it's speculation. But the idea stays in your mind. You trace the link, navigating through a maze of institutional domains and archived datasets. Finally, you find it, a file structure labeled Provisional Comet Observations, December-January batch. Inside are log files, light curve graphs, and partially processed spectral data, incomplete but real. Each file is tagged with a timestamp from before the shutdown. You recognize the comet's designation, 3I/ATLAS, C/2020 M2. The files aren't formatted neatly. Some lines of data are corrupted, others mislabeled. But fragments begin to form a pattern. The comet's brightness had increased far more than expected in its final recorded days. It wasn't a simple solar reaction or a reflection spike. It was sustained, almost rhythmic, as if the object was pulsing, brightening and fading with deliberate timing. You open the associated spectral readings. They show the presence of cyanogen, carbon monoxide and water vapor, all typical cometary compounds, but in ratios that don't match standard solar system comets. The ice appears richer in volatiles, more unstable, the kind expected only in objects that have never approached a star before. This supports the theory. 3I/ATLAS is interstellar. It came from another system entirely. You compare these numbers to known comets like Hale-Bopp and 2I/Borisov. The differences are clear. This object isn't behaving like anything we've catalogued. In one wavelength band, a faint emission line appears, an anomaly that could indicate complex organics. Not conclusive, but enough to suggest that its birthplace had chemistry capable of forming prebiotic compounds. You realize that whoever saved this archive, the unknown person behind the backup, might have preserved something extraordinary. Without them, these readings would have been lost in the administrative blackout. The more you explore, the clearer the trail becomes. The archive wasn't an accident. Each folder is labelled systematically, cross-referenced with data from other telescopes. Pan-STARRS, the European Southern Observatory, and even early observations from amateur astronomers. It looks like the work of a single dedicated individual, someone who anticipated the shutdown and quietly mirrored what they could before access was revoked. You imagine this person, maybe a mid-level data engineer, someone with administrative privileges, maybe a researcher who understood how fragile information becomes when politics interrupts progress. Perhaps they stayed late the night before the shutdown, copying directories into secure folders, leaving no trace of authorship. They wouldn't have done it for recognition, only to make sure the universe's message wasn't erased by bureaucracy. You feel a deep respect for whoever that was. In a system where data belongs to institutions, not individuals, someone chose to protect the truth. They didn't know what would be found later, only that something worth preserving was there. The deeper you go into the files, the more you notice how incomplete they are. Half of the data blocks end abruptly, timestamps jump. Some sequences have placeholder labels like pending verification or awaiting cross-calibration. It's like opening a half-finished letter from the cosmos, each paragraph cut short. But even incomplete, the data speaks. The comet was changing faster than models predicted. Its tail was thick with dust, unusually dense for an interstellar object. Something was happening, and then silence. You export the logs, store them locally, and begin charting trends. The light curves form irregular waves, but when plotted carefully, they show something almost rhythmic, a pattern hidden in the noise. Not perfect, not symmetrical, but suggestive. It reminds you of a heartbeat. You hesitate before drawing conclusions. The rational part of your mind insists it's coincidence, interference, maybe an artifact of measurement. But a quieter part of you wonders if it's more. Could the comet's internal activity be following some natural cycle, something intrinsic to its composition? Could the pattern hold information about its structure, its origin, or even its history among the stars? You note it carefully. Brightness variation interval suggests periodic internal venting or rotation-driven sublimation. Period approximately 3.8 hours. The phrase looks technical enough, neutral on the page. But behind it you feel a small thrill, the sense that you've glimpsed something forgotten by the larger system. You save your notes under a new project folder, labeling it simply, Recovered Data, 3I/ATLAS. For now, you can only go so far. You don't have access to NASA's full database or the advanced tools required to verify your findings. But you've confirmed one thing. The data is not lost. It's waiting quietly in backup drives and shadow archives, breathing through the silence. When the shutdown ends, this hidden memory will resurface. Others will see what you've seen, maybe more. They'll refine the data, compare it, test it. Science always resumes even after silence. The universe is patient. It doesn't mind waiting for us to listen again. You look once more at the light curve graph, the faint, uneven pulse of a comet that shouldn't exist. Somewhere out there, far beyond the reach of our instruments, 3I/ATLAS is still moving, still glowing, still writing its story in the background radiation of the cosmos. And deep inside these unmarked folders, untouched, unnamed, that story continues to wait for the next curious mind to open it. Because data remembers, even when we forget, and soon someone will listen again. You sit in the quiet room of an observatory, the screens dim except for one, a graph that glows faintly with numbers shifting like small waves. Every rise, every fall is a voice. It is not a sound you can hear, but a pattern you can read. This is how astronomers listen to comets, not through ears, but through instruments that turn light into rhythm, color into temperature, and silence into data. /ATLAS was never loud. It didn't burst with brilliance or streak dramatically across the sky. It whispered. Its light curve, the measurement of brightness over time, showed strange irregularities, like someone breathing unevenly in their sleep. The pattern fascinated scientists. Comets usually follow predictable brightening and fading as they approach the sun and then retreat. But this one pulsed differently. It seemed to shimmer with memories of another place. In astronomy, brightness is not just about light. It's about reflection, emission, and the story of energy. When sunlight hits a comet, the ice sublimates, turning directly from solid to gas, and releases dust into a glowing tail. That tail reflects sunlight back to us, creating the illusion of a voice across space. With 3I/ATLAS, the reflection was faint, but something else emerged. A subtle emission in wavelengths that hinted at complex molecules. It was as though the comet was releasing not just gas, but information. The instruments began to detect an infrared signature, not strong enough to form a clear image, but consistent enough to suggest organic compounds. These are carbon-based molecules, the kind found in life. It didn't mean the comet carried life, but it meant it carried the ingredients for it. You imagine this comet drifting between stars for millions of years, gathering and preserving chemistry from distant origins, a frozen archive of cosmic history. The observatory's computers translated these faint signals into visual form. Lines and curves on the screen became the comet's speech. Data transformed into language. Scientists often say, light is a messenger, and now you understand what they mean. Every photon, every particle of light has traveled across unimaginable distances to reach a detector on Earth. Each one carries a piece of the comet's identity, encoded in frequency and intensity. To listen to 3I/ATLAS was to read the diary of a traveller. As the data came in, researchers noticed the brightness curve didn't match its rotation period. Normally, as a comet spins, its reflective surfaces cause predictable variations in brightness. But 3I/ATLAS had an irregular rhythm, as if spinning unevenly or shedding material inconsistently. One theory suggested that its surface might be fractured, that internal ice pockets were venting unpredictably. Another theory proposed that its nucleus wasn't solid but loosely held together, a rubble pile drifting apart. If that were true, then 3I/ATLAS wasn't a comet in the classical sense. It was more like a cluster of memory, fragments bound by weak gravity, each piece carrying echoes of different star systems. Its voice was not one tone, but many overlapping frequencies. Each wavelength told a part of its story. Some came from silicate dust, the same kind found in planetary systems, others from frozen carbon monoxide, a molecule that evaporates only in extreme cold. It was a reminder that this object had once drifted through deep interstellar night. Scientists began to align its light curve with similar data from other interstellar visitors, like 1I/Oumuamua. The comparison revealed something subtle but distinct. Oumuamua had shown reflected sunlight with no visible tail, suggesting a rocky, possibly metallic body. 3I/ATLAS, on the other hand, showed sublimation, genuine outgassing, a proof that it was icy and active. That activity made it more comet-like, yet its motion through the solar system was far too fast to be bound by our sun's gravity. It was both familiar and foreign, a hybrid of known and unknown categories. You start to realize how much of astronomy is like eavesdropping on the universe. Scientists never truly see objects in space. They interpret what light allows. Every spectrum, every fluctuation is a form of speech. 3I/TLAS spoke slowly, its signal buried under cosmic background noise. Yet when processed carefully, it revealed consistency, not chaos. It had rhythm like a pulse that beat once every few hours, suggesting some internal structure still intact. The observatory's logs show that these observations were made just days before a major system shut down. Funding cuts and technical freezes were already looming, and teams were racing to gather as much as possible before the instruments went offline. In a way, this urgency sharpened their focus. They listened more closely, not knowing when they might hear again. As you read the reports, you begin to appreciate the patience it takes to listen to space. There are no quick answers, no instant feedback. It's a conversation stretched across centuries of light. Every discovery comes with uncertainty, and yet the process continues, listening, measuring, rechecking. 3I/ATLAS reminded astronomers of this humility. Its irregular voice was a challenge to interpret without assuming, to understand without rushing. Eventually, the collected data showed something unexpected, a faint secondary pattern layered over the main brightness curve. Some thought it might be noise. Others suspected it was a signal from rotational fragmentation, the comet breaking into smaller pieces as it spun faster from solar heating. But when cross-referenced with earlier readings, the same pattern appeared, even before it neared the sun. That meant it was intrinsic, not environmental. The comet was unstable from the beginning. This instability could explain why it brightened suddenly, and then dimmed faster than predicted. It wasn't fading from distance, it was disintegrating. The fragments, though too faint to detect individually, collectively contributed to the changing light. In a sense, 3I/ATLAS was speaking through its own decay. Its frozen voice was dissolving into smaller echoes, scattering across space. Still, even in its disintegration, the data held form. By mapping the changes, scientists reconstructed a three-dimensional model of how the comet might have looked before it broke apart. The nucleus was elongated, irregular, and covered with volatile ices. In this fragile shape lay the evidence of long travel, collisions, heating, cooling, and the wear of time. You can almost imagine it tumbling silently, carrying secrets older than our planet itself. Listening to a comet is not like listening to a star. Stars emit steady light governed by nuclear fusion. Comets are erratic, so their brightness a reflection of both physics and chance, yet this irregularity is what makes them alive in a way. Each fluctuation is a response to environment, a dialogue between ice and sunlight. 3I/ATLAS was having that dialogue across interstellar boundaries, and for a brief moment Earth was listening. When the last observation of that phase was recorded, the scientists saved their files under a quiet label, Unresolved Light Pattern. It was a name that meant both mystery and continuation. Because in science, to be unresolved is not to be lost, it is to remain open to interpretation. The room goes quiet again. You imagine the faint hum of the data servers, the steady ticking of clocks that measure both time and curiosity. Somewhere beyond our solar system, the fragments of 3I/ATLAS drift farther away, carrying their final signals into the void. But the patterns remain here, captured in numbers, archived in light, waiting to be read again. And as you lean back, you begin to sense that those patterns, those faint frozen voices, might contain more than brightness. They might hold intention, or perhaps just the mathematics of wonder waiting to be understood in a new way. Mathematics is often seen as the cold language of precision, But in the study of space, it becomes something far more alive. Every line of calculation, every curve drawn on a graph, tells a story about how the universe moves and breathes. When you look at the data from 3i/ATLAS, you don't just see numbers, you see relationships. You see how gravity speaks in equations, how speed writes itself across distance, how time folds itself into orbit. After weeks of collecting the comet's brightness data, astronomers began to transform those light readings into motion. Each shift in luminosity hinted at rotation, trajectory, and energy exchange. Using differential equations, they modelled how the comet accelerated as it neared the Sun, and how it slowed as it escaped its gravitational reach. The path wasn't a neat ellipse, like most comets that orbit our star. It was a hyperbola, a wide, open curve that never loops back. That single equation confirmed it. 3i/ATLAS did not belong to our solar system. It came from beyond. The equation for a hyperbolic orbit is simple on paper, but profound in meaning. It tells you that the object's total energy is positive, more than what the Sun's gravity can bind. The comet is free, travelling fast enough to escape any return. For astronomers, this was both a thrill and a loss. Once it left, it would never come back. Every observation mattered, because there would be no second chance. When they plotted its velocity relative to the Sun, it measured over 110,000 kilometers per hour. To put that in perspective, it meant 3i/ATLAS was moving about 30 times faster than a rifle bullet, fast enough to cross the distance between Earth and the Moon in just over 3 hours. Yet in the stillness of a computer lab, this enormous speed became a quiet line on a chart, a slope calculated to the 4th decimal. Numbers like these are deceptive. They look sterile, but they are windows into something astonishing. When you graph the trajectory of a comet, you are tracing the influence of every mass it has ever encountered, every gravitational nudge, every interstellar interaction. You're reconstructing its history and geometry. For 3i/ATLAS, the arc of its path revealed a story of deep time, a journey likely lasting millions of years, possibly beginning in a region far from our galaxy's core. The mathematics became a bridge between imagination and evidence. Through orbital mechanics, scientists could rewind the comet's path backward, not literally, but computationally, and estimate where it might have come from. The results pointed toward an origin somewhere in the outer spiral arm of the Milky Way. There, far from dense clusters of stars, interstellar objects drift in long silence before gravity from a passing system slingshots them into new trajectories. 3i/ATLAS was one of these wanderers, dislodged from its birthplace and sent careening toward the unknown. The more the team calculated, the more questions emerged. When they compared 3i/ATLAS's orbit to that of Oumuamua, the first confirmed interstellar visitor, they noticed similarities. Both travelled on hyperbolic paths, both entered the solar system from directions near the galactic plane. But their velocities and inclinations differed slightly, suggesting they weren't related, at least not directly. Still, it raised an intriguing possibility. Maybe interstellar objects are more common than once thought, quietly passing through our system all the time, unseen except by the most sensitive instruments. In the observatory logs, one researcher wrote a line that stood out. Mathematics is how we listen when the universe doesn't speak. It's true. The universe rarely offers explanations, it shows you data, and it's through numbers that patterns become visible. When the brightness fluctuated in the 3i/ATLAS readings, math transformed those fluctuations into models of rotation and fragmentation. A small variation in magnitude, barely measurable, could represent the loss of hundreds of tons of material. Astronomers applied Fourier analysis, a mathematical method that decomposes complex signals into simpler waves, to isolate periodic changes in brightness. The resulting graphs showed repeating intervals, implying the comet rotated roughly every 9.6 hours. That meant one side of the comet was brighter than the other, perhaps due to differences in composition or surface roughness. Each spin carried fragments of dust outward, forming jets that bent slightly under solar radiation. The more they analysed, the more they realised how dynamic 3i/ATLAS was. It wasn't just moving, it was changing shape. Equations that once predicted smooth decays in brightness now had to be rewritten to include sudden collapses and rebounds. To account for this, they introduced new parameters: sublimation rate, torque variation, nucleus instability. Each factor had its own uncertainty margin. The comet's mathematical portrait became a living thing, shifting every time new data arrived. The calculations also extended beyond the comet itself. Researchers used orbital perturbation theory to examine whether the object's path was influenced by unseen forces, perhaps small gravitational tugs from planets, or even pressure from the solar wind. Most influences were accounted for, but there remained a minor deviation that couldn't be easily explained. It was tiny, almost within error range, but consistent. Some suspected non-gravitational acceleration caused by asymmetric outgassing when jets of vapor acted like miniature thrusters. Others wondered if it pointed to something deeper, maybe an interaction with the interstellar dust or magnetic fields beyond current models. Mathematics didn't give definitive answers, but it gave direction. It told scientists where to look next, which variables to refine, which assumptions to challenge. It wasn't about certainty, it was about progress through approximation. The more precise the equations became, the more profound their implications. To model a comet was to understand the dialogue between matter and motion, how energy transformed across scales too vast to visualize directly. Even for someone outside the field, the beauty of these numbers is easy to feel. A single equation at v equals the square root of gm open, parenthesis 2 over r minus 1 over a close parenthesis, defines the speed of an orbiting body. Hidden inside it are gravity, distance, and destiny. It describes how something as massive as the sun can hold an object light years away in a fragile dance, or how that object can finally slip free. Each symbol, each variable, represents a force that shapes the cosmos. In late-night meetings, when data upload slowed and silence filled the observatory halls, the researchers sometimes talked about how mathematical discovery feels. They said it's not excitement that drives them, but calm recognition. Solving an equation that fits the universe is like tuning an instrument until it vibrates in harmony. It's quiet satisfaction, the feeling that somewhere, far away, nature has nodded in agreement. For 3I/ATLAS, the numbers eventually told a coherent story. An interstellar body on a one-time journey, shedding material as it passes, leaving behind a faint trail of dust and data. Its speed ensured it would soon leave the solar system forever, but its influence would remain, in models, in papers, in memory. Each calculation, carefully recorded, became part of that legacy. When you step back from the charts and equations, you see something unexpected. Mathematics isn't separate from wonder, it's the structure that allows wonder to exist. Without it, the beauty of the comet's journey would dissolve into randomness. With it, the motion becomes readable, like notes on a staff forming music. The last calculation in the logbook ends with a question mark, a reminder that precision doesn't erase curiosity. Beneath the certainty of numbers lies a deeper mystery. What if this object isn't unique? What if there are countless others like it, tracing silent paths across the galaxy, each carrying the equations of their own origin? That question lingers in your mind as you look at the final graph. It's a simple curve, nothing dramatic. Yet in its slope lies everything: the pull of gravity, the age of the universe, and the faint memory of motion between stars. You close the file, the numbers fade from the screen, leaving only the faint hum of machines, and the thought that mathematics, in the end, is not the opposite of wonder. It is its foundation. And somewhere in that foundation, hidden among equations, waits a secret curve, the one that shouldn't exist at all, the one that will lead you into the next question, the secret trajectory. When astronomers first plotted the trajectory of 3I/ATLAS, it seemed straightforward, an interstellar object on a hyperbolic path through the solar system. But as more data accumulated, the simplicity faded. The orbit didn't behave exactly as the models predicted. Something in the curve was off, not dramatically, but consistently. It was as if a small invisible force was reshaping the comet's path in real time. In astrodynamics, orbits are rarely perfect. Every gravitational field, every tiny pressure from sunlight or outgassing can distort a trajectory. But this distortion was peculiar. Even after adjusting for known variables, solar radiation pressure, jet effects from sublimating ice, and gravitational influences from nearby planets, the residual acceleration remained unexplained. It was small, measurable only in fractions of a millimeter per second squared, but too persistent to ignore. Astronomers ran simulations using high-precision ephemerides, tracking how the comet's position should evolve day by day. The actual observations drifted slightly from predictions, forming a pattern that couldn't be dismissed as random error. This deviation, first flagged by a graduate researcher during a routine orbital fit-in, became the starting point of what they later called the trajectory anomaly. At first, most assumed it was a software or calibration issue. Telescope optics can warp under temperature changes, timestamps can desynchronize, even the Earth's rotation corrections can cause millisecond discrepancies. But when multiple observatories, from Hawaii to Chile, reported the same offset, the mystery deepened. The trajectory anomaly was real. Some scientists proposed that asymmetric outgassing could be the cause. As the comet's frozen surface warmed near the sun, jets of vaporized ice might shoot unevenly, acting like miniature thrusters. This had been observed with other comets before, altering their paths slightly. However, 3I/TLAS showed less visible jet activity than expected for such an effect. Spectral readings revealed minimal water vapor emissions, too little to produce the observed acceleration. Others suggested a more unusual possibility. Maybe the surface was composed of exotic volatiles, materials that sublimated at lower temperatures than typical cometary ice. Substances like carbon monoxide or molecular hydrogen could behave this way, producing thrust even at great distances from the Sun. This theory fit the data better, but it also implied that 3I/ATLAS came from a region of space where such compounds were abundant, perhaps a cold, distant molecular cloud or even interstellar space untouched by starlight. The mathematics of its motion became increasingly complex. Instead of a clean hyperbola, the plotted path began to resemble a slightly bending arc, its curvature shifting by minute degrees as new readings arrived. To account for this, orbital modelers introduced new terms: non-gravitational acceleration coefficients, perturbation parameters, and thermal lag factors. These weren't arbitrary. They represented real forces, just ones not yet fully understood. When the team compared the data to Oumuamua, the first known interstellar object, they found striking parallels. Oumuamua had also shown unexplained acceleration, though without visible outgassing. Some had even speculated, controversially, that it might have been an artificial object, a piece of alien technology propelled by light pressure. While most dismissed that idea, the similarities were hard to ignore. 3I/ATLAS displayed the same subtle deviation, but in a different direction. It wasn't accelerating outward, as light pressure would cause, but slightly sideways, as if nudged by an unseen gravitational field. This led to long discussions in conference calls and data-sharing sessions. Could there be a small body like an asteroid or a dwarf planet exerting a gravitational pull unnoticed in existing models? Simulations ruled it out. The anomaly persisted even when all known masses were included. One particularly late night, a researcher named Dr. Lin decided to run a reverse integration, tracing the orbit backward through time frame by frame, to see where 3I/ATLAS had been years before entering the solar system. The results were odd. The backward projection showed a slight kink in its distant trajectory, a deviation occurring several light years away, as though it had passed near something massive, perhaps a star or even a rogue planet. But the region of space it came from was nearly empty, according to current catalogues. The more they tried to trace its origin, the less sense it made. The trajectory didn't point cleanly toward any known stellar system. Instead, it emerged from a region between mapped stars, a stretch of interstellar void where gravity is weak and encounters are rare. For something to be ejected from that emptiness, it must have experienced a force from something unrecorded. This led to one of the more speculative discussions within the team. What if the comet had interacted with a dark object, something massive yet invisible, like a black dwarf or a small black hole? The idea sounded far-fetched, but mathematically the numbers fit. A close pass by such an object could easily impart the velocity shift seen in the data without leaving visible traces. Still, without direct evidence, it remained an elegant but unprovable hypothesis. Amid the speculation, a smaller group took a different approach. They began mapping the comet's path using galactic coordinates instead of heliocentric ones, seeing it not in relation to the Sun but to the Milky Way as a whole. The shift in perspective revealed a subtle alignment. 3I/A TLAS's inbound vector matched, almost perfectly, with a known galactic magnetic filament. That was surprising. These filaments, vast threads of charged particles and magnetic fields, stretch across interstellar space, influencing how dust and gas drift. If 3S/a TLAS had travelled along one, it might explain its peculiar motion. The idea of magnetic guidance wasn't new, but it was rarely considered for solid bodies like comets. For it to be possible, the comet would need to contain ferromagnetic material, metals capable of responding to magnetic forces. Later spectroscopic readings hinted that 3I/a TLAS's dust contained traces of iron and nickel. In theory, that could make it susceptible to long-term low-level magnetic influence during its interstellar voyage. Still, in theory wasn't proof. The anomaly remained. Every time they thought they had isolated the cause, another inconsistency appeared. Some began to joke that the comet was simply unpredictable by nature, a traveller from another system that refused to obey ours. But beneath the humour was quiet unease. If an object's motion couldn't be fully explained by known physics, it meant there was something missing in our understanding of how the interstellar space shapes matter. Over time, as the comet moved farther from the Sun, the acceleration diminished. The deviation grew smaller until it was almost indistinguishable from background noise. Some saw that as closure, others as a clue that the effect was local, tied to the environment near the Sun, or to something transient that had passed. In the final reports, the anomaly was given a name: non-gravitational component delta sub n. A single line in a table summarized months of work and uncertainty. But for those who had followed its path from the beginning, that line meant more than data. It represented the moment they realized that even precise science can encounter the unknown. When you look at the plotted trajectory now, it's a smooth curve across a dark background. Yet behind that curve lies the story of endless questioning. A reminder that space is never truly empty, and that even a wandering comet can carry the fingerprints of forces we still don't understand. And as you think of that path, bending slightly, persistently, you begin to wonder, if this one object carries unexplained motion, how many others have passed unnoticed, their secret trajectories still hidden among the stars? When the servers went offline, silence filled the research center. The night monitors sat in front of blank screens, their reflections staring back. For a few moments they thought it was maintenance, but then, one by one, the databases failed to respond. The links between observatories went dark, backups that should have synced automatically stayed frozen. Something larger than a routine outage was happening. You could feel it, not panic, but a hollow uncertainty, as though part of the universe had been erased. At first, the loss seemed technical. Power surges, failed scripts, incomplete transfers, all normal in a system stretched across continents. But when the engineers restored partial access, they found gaps, entire blocks of observational data missing. The most recent readings from 3I/a TLAS had vanished. Files from the previous week, backup logs and comparison charts were either corrupted or inaccessible. The comet's final recorded path before the blackout was gone, as if the sky itself had withheld that fragment of truth. Astronomers searched external drives and mirrored servers, tracing the data's journey. Some files reappeared in fragments, partial frames, distorted light curves, incomplete temperature readings. Others were overwritten by noise. A few copies survived only because small local observatories had their own systems offline during the outage. Those independent stations, forgotten during funding cuts, now held what global systems lost. It was as if the universe had chosen unlikely custodians for its secret. The recovery process began quietly. Technicians pulled data from shadow directories and redundant caches. Every byte was examined manually, stitched together like torn pages of a cosmic diary. It took weeks to identify the patterns of damage. Some files carried timestamp mismatches, others showed edits that didn't match any logged operator activity. The deeper they looked, the stranger it became. The gaps weren't random, they followed the path of the comet itself, as though the erasure had intent. Rumours spread quickly across research channels. Was it a system failure or deliberate interference? The timing was too precise. The data loss aligned almost exactly with the beginning of the government shutdown. Officially, the explanation remained simple: power disruptions during transition protocols, but many scientists were unconvinced. The deleted records contained spectral data from wavelengths that hadn't yet been released to the public. It was information that could reveal new details about the comet's core composition. Losing it meant losing the ability to verify previous findings. The independent teams didn't stop. They worked through nights, reconstructing frames pixel by pixel. Each image, though blurred and incomplete, told a fragment of the comet's story. You watched them adjust brightness curves and rerun simulations. They compared what was left to older reference points from the Pan-STARRS telescope and smaller amateur observations. Slowly, a picture began to emerge again, and not complete but alive. The comet's trajectory, brightness, and tail morphology could still be estimated with reasonable accuracy. The most revealing discovery came from metadata, not the images themselves. Timestamps embedded deep within file headers showed unusual delays between frames. It was as if the comet had briefly changed velocity, something physically improbable given its size and distance. The missing segment of data covered exactly that anomaly. Without the numbers, no one could confirm if it was a true acceleration or a measurement glitch. That uncertainty became the center of debate, a void in knowledge that drew everyone's attention. As systems came back online, internal reports circulated quietly. A few administrators admitted that several of the missing files had been manually flagged before the outage, placed in restricted directories awaiting review. Whether for security or confidentiality, no one could say. The researchers working under temporary access agreements noticed subtle changes: new user permissions, higher encryption levels, and delayed update schedules. It felt less like technical caution and more like containment. Still, science moves through persistence. Archived telescope data from other observatories filled some blanks. Amateur astronomers worldwide began uploading their own captures of 3A/A TLAS to open forums. What had once been a centralized study became a global collaboration born out of absence. Each shared image carried a time code, a small act of defiance against disappearance. You joined the reconstruction effort, watching as hundreds of volunteers compared star fields and adjusted coordinates to rebuild the comet's lost path. The deeper the restoration went, the clearer it became that no single source of truth existed anymore. Every recovered file told a slightly different version of the same night sky. Tiny calibration errors compounded into conflicting interpretations. Some scientists focused on the comet's composition, others on its motion. A few simply wanted to know why the records had been removed at all. The debate stretched beyond science into philosophy. How much of truth survives after deletion? When evidence vanishes, what defines discovery? Eventually, a nearly complete data set emerged from the chaos. Though not perfect, it was enough to continue analysis. The reconstructed timeline suggested that during the blackout window, 3I/A TLAS brightened unexpectedly, then dimmed faster than predicted. This fluctuation, if confirmed, could point to surface outgassing or fragmentation, processes that change the comet's shape and speed. The missing files might have contained the proof. Their absence left only inference and speculation. When the recovered data was recompiled, the comet's signal returned faintly but steadily. It wasn't as clear as before, yet it was something real, a reminder that information, once observed, rarely disappears entirely. Somewhere copies still existed, encrypted, misplaced, or perhaps archived beyond access. The universe has its own way of keeping records. Every photon scattered from that comet still travels outward, carrying the evidence of what happened. Maybe someday another world will receive it intact. You sit in front of the restored visualization, watching the comet drift across a digital sky rebuilt from fragments. Each pixel represents patience, cooperation, and curiosity. The loss had forced humans to act like the cosmos, resilient, self-repairing, unwilling to let information die completely. In that effort, science became more than observation. It became remembrance. And as you stare at the reconstructed light, a question grows quietly in your mind. If lost data can return, what else, hidden in longer wavelengths, might still be waiting to be heard? Visible light tells us what our eyes can understand: color, brightness, reflection. But when astronomers shifted to infrared observation of 3I/A 3I/ATLAS, the picture changed completely. What seemed like a cold and dim object in visible wavelengths became alive in heat. The instruments detected faint emissions that ordinary telescopes had missed. The comet, cemented in normal light, began to reveal itself in the invisible spectrum, like a photograph developing under chemical reaction. Infrared imaging is more than color substitution. It's an entirely different language of data. It translates temperature into light and silence into signal. The first readings from the infrared sensors showed irregularities, patches of warmth where none should exist, slight differences across the surface temperature that suggested active processes. For something thought to be inert and ancient, that was unexpected. The comet was not just reflecting sunlight, it was generating its own small variations in heat, possibly from internal reactions. The research teams began aligning the data from multiple telescopes. Each wavelength revealed another layer of information. The visible spectrum showed the general outline, a pale, elongated body with a fading tail. The infrared spectrum showed internal structure, hidden fractures, heat signatures, and active regions. It was like comparing a human's photograph to an MRI scan. What had once been a distant speck now appeared textured and complex. Scientists working with spectroscopy data found something even more surprising. The reflected infrared wavelengths indicated the presence of organic dust, carbon-based compounds similar to those detected in other comets and meteorites. But the ratios were different. There were traces of complex hydrocarbons that normally form only after long exposure to radiation or heat. 3I/ATLAS seemed to have traveled through areas of intense cosmic activity, gathering molecular scars along the way. That discovery placed it in a rare category of interstellar objects, not just a wanderer, but a messenger carrying chemical history between star systems. The next challenge was to confirm the readings. Interference from Earth's atmosphere often distorts infrared data, so teams cross-referenced space basin telescope results from the Spitzer archives and newer ground-based sensors with adaptive optics. When the comparison aligned, the results became undeniable. The comet's surface was laced with materials capable of retaining warmth far longer than expected. That meant its composition was not uniform. It had absorbed layers from multiple origins, possibly colliding with other interstellar dust clouds during its journey. The study turned from curiosity to revelation. The thermal variations implied that parts of the comet might still be releasing trapped gases. These outgassing points, though faint, could alter the comet's spin or trajectory over time. Small bursts of sublimation, ice turning directly into vapor, would change the balance of forces acting on it. This could explain the slight deviations previously observed in its path. It was not a passive object. It was changing as it traveled, adjusting to new environments even in deep space. For astronomers, the implications were enormous. If 3I/ATLAS carried complex organic molecules, it might be a small piece of cosmic transport, a carrier of prebiotic material across galaxies. These molecules, once delivered to a planet or moon, could contribute to chemical processes that eventually lead to life. It didn't mean the comet was alive, but that it carried the potential ingredients for life's beginnings. That idea transformed the study from pure observation to existential wonder. The researchers compiled spectral graphs showing peaks where the organic dust absorbed specific infrared wavelengths. Each peak corresponded to chemical bonds found in carbon chains, alcohols, and amino precursors. What amazed them most was how clean and stable the readings were despite the distance. It meant the comet's material had been preserved exceptionally well, shielded by outer layers of darker, denser dust. The protective crust acted like insulation, keeping the fragile compounds intact for millions of years. As the data analysis deepened, the team realized they were witnessing an ancient record. Each infrared emission was a form of memory, energy escaping from substances that had survived cosmic radiation and collisions. By studying the heat patterns, they could trace where the comet had been: regions of intense starlight, areas of gravitational stress, and long stretches of cold silence. The object had traveled across different zones of the galaxy, collecting its current structure as a geological timeline of space itself. Meanwhile, the visible images continued to fade. The comet's brightness in ordinary light was dropping rapidly as it moved farther from the sun, but in infrared, it remained detectable long after optical instruments lost track. That endurance was the key. It proved that the object's true nature existed beyond human vision, in wavelengths that recorded the faint breath of ancient heat. It was like hearing an echo after the sound had already gone. At NASA's Infrared Analysis Lab, the reconstructed image of 3I/A TLAS became a case study in multispectrum observation. Researchers layered visible, infrared, and radio data to create a composite model. The result was a detailed map of temperature gradients, showing how sunlight penetrated and re-radiated through the comet's crust. This model helped estimate how long the comet had been exposed to interstellar environments and how its materials evolved under cosmic radiation. A few scientists noticed something else: small, consistent fluctuations in the long-wavelength data, repeating over hours. It wasn't noise, it resembled a pattern, not artificial but rhythmic, possibly caused by rotation or a periodic release of heat. The team used mathematical models to confirm that it matched a regular spin interval. 3I/A TLAS was turning slowly, like a giant clockwork fragment drifting through emptiness, keeping time through temperature. By the end of the analysis, a clearer truth emerged. The light we see shows beauty, but the light we don't see shows history. The comet's infrared voice was steady, informative, and ancient. Every emission line represented endurance, the persistence of material across impossible distances. What had been dismissed as a faint, frozen object turned out to be a living archive of interstellar chemistry. When the last simulation finished rendering, the screen glowed faintly with red and orange patches, heat signatures mapped from data. The researchers stared quietly. In that silent warmth, they found a kind of evidence not written in words or symbols. The universe was speaking, not in brightness, but in temperature. You realize then that even silence carries creation. Not every message from the cosmos comes as light visible to the eye. Some speak through the soft hum of infrared radiation, the faint warmth of something that has traveled farther than imagination, still glowing enough to be found. Astronomy is not only about discovery, it is also about patience. Observing something as distant and faint as 3I/A TLAS requires long hours of stillness, careful calibration, and trust in data that may take days to confirm. Astronomers spend much of their time not looking through telescopes, but at screens filled with graphs and pixelated readings. In that environment, silence is part of the process. It's not the absence of sound, but the background in which understanding slowly appears. At NASA's data center, the atmosphere was steady and deliberate. Scientists took turns monitoring the infrared, optical, and radio feeds, ensuring that no small fluctuation went unnoticed. Most nights they waited for hours just to confirm a tiny variation in brightness or a new data packet from a satellite telescope. Each observation had to be checked for interference, corrected for Earth's rotation, and compared with prior results. The work demanded precision and endurance, not excitement. Progress came in the form of a verified number, not a revelation. One researcher described the process as listening with instruments. They were not measuring noise in the conventional sense, but reading patterns that emerged from vast stretches of nothing. Between two data points was where the story lived. A signal could be weak, delayed, or incomplete, but its consistency over time mattered more than its strength. That was the discipline, learning to find significance in repetition and reliability. The team working on 3I/A TLAS learned early that the comet's faint glow was almost always hidden within background radiation. The detectors had to be tuned to isolate the smallest fluctuations in intensity. Every adjustment meant recalculating calibration constants, realigning sensors, and synchronizing observation logs. It was repetitive work that demanded full attention. Yet without this steady, almost invisible labor, the broader conclusions about the comet's structure would have been impossible. In many ways, the people handling the data were performing an art as much as a science. They couldn't force the universe to speak faster. They had to wait for light that had already traveled for years to reach them. Some nights, clouds interrupted the ground-based observations, forcing pauses in data collection. Instead of frustration, the team used those breaks to analyze previous results. They noticed subtle changes, a faint shift in temperature distribution, a gradual dimming of the tail, details that would have been lost in haste. Silence, in this setting, wasn't a problem. it was a condition for accuracy. When all instruments seemed quiet, the researchers checked background metrics, confirmed baseline readings, and compared timestamps across systems. In that process, they found patterns that looked like nothing at first: gradual drifts, smooth slopes, low-frequency variations. Over time, those small findings formed the foundation of a larger understanding of how the comet behaved as it moved farther from the Sun. Several young astronomers were assigned to manually review observation logs, matching data points by hand. It was tedious, but it taught them to recognize natural irregularities from system noise. They learned how to distinguish a real cosmic signal from an instrument error, a skill that algorithms still struggled with. Their notes filled pages of temperature readings, signal strengths, and small anomalies. Some of those manual corrections later turned out to be essential for interpreting the comet's true trajectory. The project's lead scientist often reminded the team that every gap in the data is part of the data. A missing entry wasn't failure, it was a marker of how fragile the process of observation could be. Space doesn't offer second chances. If a transmission is lost, it might never repeat. That awareness made everyone more deliberate. Each measurement was treated as a rare opportunity to glimpse something that might never appear again. The researchers began to see silence as a form of communication. When the instruments registered nothing, it meant stability. When readings fluctuated, it meant activity. Both carried meaning. The absence of a spike could indicate that the comet had entered a quieter phase of its journey, releasing fewer gases. A small surge could mean sunlight had reached a previously shadowed surface. Every detail was a clue to the object's evolving state. Over time, the practice of patient observation created a rhythm in the lab. The team grew accustomed to long intervals of stillness punctuated by small bursts of discovery. A new data file arriving from a telescope in Chile could shift the entire mood of the night. They would gather around screens, analyzing pixel maps of faint red and blue dots that represented light scattered across millions of kilometers. To outsiders, it looked uneventful, but to them, it was the sound of progress. In a field where precision is everything, emotion has little place in analysis. Yet even the most experienced scientists admitted that moments of clarity felt profound. When the data aligned perfectly after weeks of processing, there was a quiet satisfaction in the room, not cheering, just acknowledgement. The numbers had meaning now. They represented a distant reality made measurable by human effort. As the study continued, the team realized that their work depended as much on restraint as on curiosity. Rushing interpretation led to errors, waiting led to truth. The silence between measurements was not wasted time, but an essential part of the process that let understanding settle and mature. The comet's faint signals were not loud, but they were steady, and steadiness is what science listens for. In the end, the hands that measured silence were not just collecting data, they were refining a way of seeing. The astronomers' patience turned invisible light into knowledge. Between the lines of numbers, between the gaps of data, they found something enduring, proof that the universe, even in its quietest moments, is still communicating. The more scientists studied 3I/ATLAS, the clearer it became that the comet was a messenger from somewhere far beyond our solar system. Its composition didn't match any of the comet's catalogue since the beginning of modern astronomy. Its orbit showed that it wasn't bound to the Sun. Instead, it was just passing through, a visitor from another system, carrying the history of a place no one had ever seen. Every molecule of ice and dust on its surface held information about conditions billions of years old, from a region of the galaxy that no telescope could directly observe. Interstellar objects like 3I/ATLAS are rare. Before it, only two confirmed examples existed, Oumuamua and 2I/Borisov. Each offered a brief glimpse into other solar systems, but their visits were too short to study in detail. 3I/ATLAS, however, lingered just long enough to allow deeper analysis. Its slow trajectory through the inner solar system gave astronomers months of observation time, enough to collect data on its structure, composition, and changing behavior. That opportunity made it one of the most scientifically valuable discoveries in recent decades. Using spectroscopy, researchers determined that the comet's ice contained a mixture of water, carbon monoxide, and complex organic compounds. These materials are common ingredients for planets and life, but their specific ratios in 3I/ATLAS didn't match any known solar system pattern. That suggested that it had formed under different stellar conditions, perhaps near a red dwarf star, or in a cluster of young suns where radiation exposure shaped its chemistry differently. Each reading hinted at a unique story of origin written into the comet's frozen surface. In a laboratory at the Goddard Space Flight Center, analysts compared the spectra of 3I/ATLAS with archived data from comets such as Halley and Hale-Bopp. The differences were clear. Where typical comets showed strong water signatures, 3I/ATLAS revealed unusually high levels of carbon-bearing compounds. That imbalance suggested a birthplace far from intense starlight, perhaps in the colder regions of an ancient stellar nursery. Over time, gravitational interactions could have ejected it into interstellar space, where it drifted for millions of years before entering our solar system. The realization that this comet had traveled across the galaxy changed how the team viewed it. It was no longer just an object of study. It was a fragment of memory, a piece of another world. Each dust particle was like a page from an ancient record, describing the physical conditions of a star system long gone. Even its imperfections, tiny cracks and irregularities, carried information about how it had survived cosmic collisions and radiation exposure during its long journey through the void. To understand its movement, scientists reconstructed its past trajectory. Simulations suggested that it might have passed through the galactic disk several times, occasionally disturbed by the gravity of stars it passed near. Each encounter altered its velocity slightly, sending it into new paths. The data implied that 3I/ATLAS could have been wandering the galaxy for hundreds of millions of years. That made it older than human civilization, older possibly than the Earth's first complex life. In that sense, it was a moving time capsule, older than anything humanity had ever touched. As they studied it, researchers found themselves reflecting on what it meant to receive something so old and distant. The comet wasn't sending a message intentionally, but its very existence was communication, evidence that matter, once formed, never truly disappears. It travels, transforms, and sometimes arrives in places it was never meant to be. The dust that clung to 3I/ATLAS could someday join another planet's atmosphere, another star's system, or even the surface of a future spacecraft. The universe reuses everything. Nothing is truly lost. Among the data collected were micro-variations in the comet's light curve. These small fluctuations indicated surface features, rotating ridges, exposed ice patches, and uneven layers of dust. Each variation helped build a more complete image of its form. The shape models showed a slightly elongated body about 2 kilometers wide, tumbling slowly as it moved. This tumbling pattern might have been caused by past collisions or uneven heating as it passed near stars. Either way, it gave the object a personality of motion, not chaotic, but restless, shaped by time. Astronomers noted that the dust released by 3/ATLAS contained silicates similar to those found in meteorites on Earth, but with subtle isotopic differences. Those differences pointed to its foreign origin. The idea that these grains could be older than our Sun fascinated scientists. Some of them joked that humanity had just received a sample from another civilization's building materials, not intentionally, but through natural processes billions of years in the making. That idea wasn't fantasy. It was a scientific possibility grounded in evidence. Even after the comet faded from visibility, the data continued to reveal new details. The archived spectra were reanalyzed using improved models, uncovering signals of frozen methane and traces of nitrogen compounds. These discoveries added new depth to its story. Each new layer confirmed that 3I/ATLAS had formed under environmental conditions unlike those of our solar system. It became a bridge between worlds, not through technology or communication, but through shared material existence. For the team, the work carried emotional weight. They weren't just looking at numbers, they were interacting with something that had traveled across interstellar space for eons. The knowledge that this object might never return, that it would continue into the darkness once more, added urgency to every observation. Each measurement felt like a conversation that could end at any moment. As 3I/ATLAS moved farther from the sun and its brightness declined, the researchers knew their time was running out. Yet the data they had gathered would outlive them. preserved in archives for future generations to reinterpret with better tools. What they had captured wasn't just a set of readings, it was evidence of how connected the galaxy truly is. Between stars lies not emptiness, but memory, carried by the fragments that move between them. When the last visible traces faded from telescope images, the scientists felt both accomplishment and loss. They had learned much, but the comet's origin remained partly unknown. It had given them a glimpse, not a full story. And as it drifted beyond their reach, they wondered what other memories might still be travelling through space unseen, waiting for the next discovery to bring them briefly into the light. When NASA first released the data on 3I/ATLAS, everything looked like another interstellar visitor, nothing more than a fragment of rock and ice passing through the solar system. But buried in the deeper analysis were irregularities, numbers that didn't fit the expected models. At first, the anomalies were dismissed as calibration errors, small misalignments in the instruments, or perhaps data corruption from solar interference. Yet the same anomalies appeared across multiple observatories, each confirming what the others had quietly found. The object's acceleration wasn't behaving normally. It wasn't following a purely gravitational path. That single fact began to unsettle people. Non-gravitational acceleration often means outgassing, jets of gas released as ice sublimates. But 3/ATLAS showed no visible jets, no trace of material leaving its surface. It moved as if propelled by something unseen. NASA's analysts debated this behind closed doors, and internal memos began to circulate using terms like non-Newtonian drift and energy asymmetry. Scientists hate uncertainty more than they fear being wrong. To say we don't know is acceptable, to say it defies our models is terrifying. So the official reports became cautious, data tables were published with rounded figures, interpretations trimmed of speculation. The public saw only what was safe, a comet-like object, faint, fast and curious. But inside the teams that studied it, the question grew sharper. What was causing the acceleration, and why did its signal pattern look structured, almost rhythmic? During one internal review, a scientist pointed out that 3I/ATLAS's brightness curve pulsed at near regular intervals. "It's like a rotation," another replied, but the periods didn't match any natural spin pattern. Some joked nervously that it was talking in light. The laughter was short-lived. NASA had already been through this kind of speculation with Oumuamua, and they didn't want a repeat of the media frenzy. Words like artificial or engineered were forbidden in official documents. A few researchers pushed for transparency, arguing that suppressing the data would only fuel conspiracy theories later. But others warned that premature release would cause panic, misinterpretation, and wild theories that it could overshadow genuine research. "This is how science loses credibility," one senior official said. "We show what we can prove, not what we fear." As days passed, internal emails revealed frustration. Observatories outside NASA's jurisdiction, ESA, JAXA, and smaller private telescopes, were beginning to publish their own measurements. The anomalies were too consistent to ignore. The object's reflectivity suggested a surface smoother than expected for a comet. Its infrared spectrum hinted at metals mixed with organic compounds, something rarely found together in such ratios. NASA quietly requested a communication freeze on public commentary until further peer review could be done. You imagine the room where that decision was made, the long table, the quiet tension, screens filled with scrolling numbers, scientists, engineers, and administrators, all staring at something they couldn't fully explain. Not a crisis, not an alien signal, but a kind of unknown that shakes the foundations of certainty. Someone must have asked, what if this changes everything we think we know about interstellar material? And someone else must have replied, then we better be sure before saying it aloud. Behind the silence, work continued. High-resolution simulations ran through the night, trying to replicate the object's motion with different parameters: sublimation rates, radiation pressure, magnetic fields, none matched. The best-fitting model included an unknown external force, something faint, consistent, and directional. "It's as if sunlight alone isn't accounting for it," one researcher noted. "Something else is pushing it." The fear wasn't about danger. It was about what it might mean if the universe contained mechanisms or designs beyond human comprehension. Discovery often begins as awe, but matures into caution. NASA wasn't hiding proof of life or technology. They were protecting science from itself, from the tendency to leap before confirming the ground beneath. When the public asked for updates, the press releases were brief. Analysis ongoing. No significant deviation detected. But within the data archives, raw numbers told another story. The pattern persisted. It wasn't random, it wasn't noise, and so the silence grew deliberate, a pause between understanding and belief. In that space of restraint, you can almost feel the weight of knowledge pressing against secrecy. Not all truths are hidden because of conspiracy. Some are held back because the human mind needs time to expand before it can hold them. NASA's fear was not of discovery, but of misunderstanding. You think about that often, that truth itself can have gravity. It bends perception, distorts expectation, and pulls everything toward itself until resistance breaks. Maybe one day those files will be released in full, every dataset, every unedited waveform. Maybe one day the world will read the line that made a scientist pause, look up and whisper, "This shouldn't be possible." Until then, the data rests, encrypted and preserved, and the silence that follows is not denial, it's reverence. After the internal debate at NASA, the project entered a quiet phase. Officially, 3I/ATLAS was still under review, but everyone involved understood that under review really meant under censor. The data files were locked behind restricted access. Only a handful of senior astrophysicists were permitted to run new models. The teams that had once collaborated freely now communicated in coded phrases, afraid that a misplaced comment could draw attention. In science, secrecy is rare, but when it happens, it carries weight heavier than gravity itself. The strange thing was that nothing about 3I/ATLAS looked dangerous. It wasn't on a collision course, wasn't emitting radiation, and wasn't behaving in a way that suggested it posed any threat. Yet the deeper the researchers went, the more the numbers seemed to whisper contradictions. Its trajectory was precise but subtly self-correcting, as if some internal mechanism adjusted its path. The idea was absurd, rocks don't steer, but the data didn't care about disbelief. One night, a junior analyst noticed that the comet's spin rate shifted ever so slightly after solar wind peaks. The expected reaction should have been chaotic, but instead it stabilized. "It's like it compensates," she said to her supervisor. The supervisor told her not to log that observation. It wasn't that he didn't believe her, it was that believing her would demand an explanation no one could provide. The next morning, that section of the dataset was redacted for further verification. Among the scientific community, rumors began to spread. People working on unrelated missions whispered about the silent project at NASA, a study that couldn't be discussed, involving an object that wasn't behaving like anything known. Some claimed the secrecy was due to national security, others thought it was an interagency dispute over data ownership. A few joked that maybe it was aliens again. But behind every joke was unease. The truth was simpler and stranger. The more they studied 3I/ATLAS, the more they found relationships between its movement and gravitational fields it passed through. It wasn't just being pulled, it was responding, small accelerations, minor deviations, each perfectly timed to balance the pull of nearby bodies. The word adaptive appeared in internal notes more than once, but it was quickly removed from later reports. The researchers didn't want to assign intention to an object that might just be an anomaly of physics. Gravity, in its pure form, is predictable. It doesn't change its rules. So when something appears to bend those rules, it forces scientists to consider possibilities that border on the philosophical. Maybe gravity wasn't bending. Maybe their understanding of it was incomplete. The secrecy, in a way, became a shield, protecting not the data, but the fragile boundary between known and unknown. Inside mission control, the atmosphere changed. The excitement of discovery had turned into the discipline of containment. Scientists worked longer hours, running simulations that often led nowhere. Some tried to publish side papers on gravitational anomalies in unrelated systems, just to explore their theories without mentioning the comet. Others left the project entirely, frustrated by the lack of transparency. One astronomer reportedly said, "We're orbiting our own silence." Meanwhile, the comet drifted farther away, slowly exiting the inner solar system. As its light faded, the mystery grew colder, like embers cooling in the dark. Every new piece of data raised more questions than it answered. Some began to suspect that the object wasn't extraordinary at all, that human interpretation had exaggerated the strangeness. But others kept digging, convinced that something fundamental was hidden in its motion. A physicist named Dr. Keller ran an independent model that combined gravitational lensing effects with the object's reflectivity changes. What she found unsettled her: a consistent correlation between its position and variations in local space-time curvature. It was as if 3/TLAS didn't just follow gravity, it subtly influenced it. When she presented the model to her team, they told her to delete it. The implications were too wild, too untested. But Keller didn't delete it. She copied the files to a private drive and quietly resigned from the project a week later. You think about her decision, the quiet defiance of a scientist who refuses to let data be buried. Maybe she wasn't trying to expose a secret. Maybe she was trying to protect the truth before it got rewritten. Secrets, after all, have their own kind of gravity. The more you try to hide them, the stronger they pull on those who know. By the time 3/TLAS moved beyond the reach of Earth's most powerful telescopes, its legacy had already split in two. There was the official record, a faint, fast interstellar comet with unexplained deviations, and there was the unspoken version, the one held in whispers, encrypted files, and resigned scientists' memories. The project ended quietly, without ceremony. No announcement, no closure. The archived data was stored in NASA's Deep Research Network under a generic label. Only a few people still remembered what it truly referred to. Years later, when an inquiry was made about revisiting the dataset for a new interstellar study, the request was denied. The reasoning was simple: incomplete telemetry, insufficient verification. But you can almost sense that wasn't the real reason. Maybe the universe hadn't finished teaching what that object meant. Maybe humanity just wasn't ready to understand it yet. In the end, gravity didn't just hold the comet, it held the truth about it. Somewhere in those encrypted archives lies a record of the moment when science brushed against something vast and unexplainable. And just like gravity, that truth keeps pulling silently toward revelation. When the research into 3/TLAS finally slowed, what remained wasn't disappointment, it was quiet. The scientists who had once argued over theories and models now sat in front of their screens, reading incomplete data sets like pages missing from a book. The excitement had faded into something subtler: reflection. For months they had tried to extract meaning from noise, light, and uncertainty. Now they began to realize that the absence of information was information itself. Every telescope has blind spots. Every signal, no matter how precise, carries distortion. When 3/TLAS moved beyond observation range, those blind spots expanded, and researchers faced a truth they didn't often discuss. Science isn't about knowing everything. It's about learning from what cannot be known. One astronomer said during a late-night debrief, "The silence between measurements teaches more than the measurements themselves." That statement, meant as comfort, became something like a mantra in the department. The project archives were still being reviewed, but no new data would come. The comet's faint signature had faded beyond detection. Even the infrared sensors, once able to trace residual heat, reported only background radiation. Some saw this as failure. Others saw it as closure. For many scientists, the lack of progress forced them to reconsider their methods. How much of what they believed depended on confirmation? Could they appreciate patterns that existed only in fragments? A physicist named Liu proposed a study on data gaps, specifically what missing intervals might reveal about the system itself. She discovered something unexpected. The missing data points often aligned with solar flare activity and magnetic field shifts. It wasn't proof of a new phenomenon, but it hinted that even voids had behavior. That idea, measuring absence, became her focus. Within months, her paper on quantifying the unrecorded circulated quietly among the team. It was less about 3/TLAS and more about the philosophy of research itself. At NASA's Analysis Center, the environment began to change. Without constant urgency, there was room for slower, deeper thought. The scientists who had burned out during the comet's tracking now took long walks, revisiting their motivations. Some admitted that the silence was harder to face than the unknown. They were trained to analyze light, not darkness. Yet now, darkness was all they had left to work with. When the weekly review meetings continued, they no longer focused on numbers. Instead, they discussed patterns of uncertainty, why human interpretation often tries to fill gaps instead of accepting them. They reviewed older interstellar events, comparing how previous teams had handled incomplete data. In those discussions, a quiet wisdom emerged. Understanding isn't always about more information. Sometimes it's about accepting limits. The younger analysts found that lesson difficult. They wanted answers, closure, something definite to write into reports. But the senior researchers began mentoring them differently. If the data doesn't speak, one said, don't force it. Let it rest. The universe doesn't owe us an explanation every time. It wasn't cynicism. It was maturity born from years of studying phenomena that refused to fit neatly into theories. Meanwhile, a side project emerged from the silence. A small team started building a simulation using the incomplete data, filling gaps not with assumptions, but with patterns observed from other comets. They called it the reconstruction model. Its purpose wasn't to replace the lost information. It was to visualize the limits of what could be known. The simulation showed how missing light curves and trajectory deviations shaped understanding, like shadows revealing the presence of an unseen object. The model became strangely popular within the department, not because it solved the mystery of 3I/ATLAS, but because it represented a new way to engage with uncertainty. One of the researchers said, "We can't hear the comet anymore, but we can hear the silence it left behind." That comment, though metaphorical, reflected how the project had evolved, from pursuit of discovery to contemplation of meaning. As months turned into years, most of the team moved on to new assignments. Missions shifted focus to exoplanets, deep space mapping, and asteroid defense, yet the legacy of 3I/ATLAS lingered. Every now and then, a new intern or data scientist would stumble upon the archived files and ask why the telemetry stopped so abruptly. The veterans would smile and say, "That's the part where it taught us the most." You can imagine those files now, lines of code, partial graphs, timestamps fading into nothing. To an outsider, it would look like an unfinished project. But to those who worked on it, it was a complete lesson in humility. The silence wasn't empty. It was structured, consistent, and deeply instructive. It revealed how humans project meaning onto noise, and how discovery often lies not in finding something new, but in learning to listen differently. By the end, the phrase science of silence began appearing informally in reports and even in lectures. It described a mindset, an understanding that not every observation needs resolution. Sometimes the universe simply stops speaking in measurable ways, and the responsibility of the observer is not to fill the gap with assumptions, but to preserve its shape. That was what 3I/ATLAS ultimately left behind. A sense that knowledge has boundaries, and within those boundaries lies beauty. The data might have ended, but the thinking it inspired continued to ripple through scientific circles. Silence became not the absence of discovery, but a form of discovery itself, and for the people who had once tracked a frozen traveller from another star, that realization was enough. It began with an alert from one of the smaller observatories. The automated system flagged a sudden increase in brightness from a region of the sky associated with the last known trajectory of 3I/ATLAS. The change lasted less than 2 minutes. At first, the team thought it was a sensor error, a glitch caused by background interference or a calibration drift. But when 3 other instruments confirmed the same anomaly, everyone knew something unusual had happened. The universe, it seemed, had blinked. The term blink became the shorthand in internal reports. No one could agree on what had caused it. The spike was brief but clean, too consistent to be random noise. Some suggested it might be a solar reflection off a rotating fragment of ice, while others proposed a release of volatile gases. But the most intriguing detail was its pattern. The brightness didn't just rise and fall, it oscillated in a repeating rhythm before vanishing completely. That rhythm caught attention, because nothing about it matched the expected decay of cometary light. Over the following days, the analysis teams across different facilities began cross-checking timestamps. Every telescope that had recorded the event, from infrared sensors in Hawaii to radio receivers in South America, showed the same temporal structure. The pattern wasn't localized to one observation band. It was visible in infrared, faintly detectable in optical, and hinted in radio frequencies. That meant the event was real, not a digital artifact. The data showed that for precisely 96 seconds, the reflected light from that region varied in intensity with measurable consistency. The fluctuations followed an almost mathematical spacing. "It's like a pulse," one researcher commented. Others compared it to a heartbeat, though everyone was careful not to romanticize the finding. Still, the metaphor lingered, because after months of silence, something had spoken, even if only once. The timing of the flash drew immediate attention at NASA. It coincided with a scheduled deep sky survey that was operating on backup systems during a partial network outage. The coincidence worried some people. If it had been a little later or earlier, the event might never have been recorded. That fragility, the idea that the universe had revealed something for less than 2 minutes and that it could have been missed, gave the moment an almost haunting quality. Scientists don't usually talk about luck, but this time many did. Once the data was cleaned and normalized, the modeling phase began. Several teams simulated what could cause such a pattern. One possibility was that a piece of the comet's nucleus had fractured and was rotating rapidly, reflecting sunlight at precise intervals before drifting beyond illumination range. Another theory proposed that it was the result of a sudden expulsion of material, a cryovolcanic burst, from residual ice pockets deep within the comet's structure. However, that theory conflicted with the expected temperature at its distance from the Sun. By all standard models, 3/ATLAS should have been completely inert by now. The anomaly triggered renewed public interest. News outlets ran the headlines suggesting that the lost comet speaks again, but inside the agency, researchers remained cautious. They remembered the media frenzy around the earlier phases of the discovery and didn't want to repeat it. Instead, they approached the event as a chance to refine their understanding of how interstellar objects behave once they leave solar influence. One of the senior astronomers, Dr. Elena Navarro, led the review committee. Her team noticed that the light curve's symmetry didn't align with natural outgassing events. The rhythm was too structured, like something modulated rather than chaotic. They ran Fourier analyses and frequency decompositions, treating the data as if it were a signal rather than random variation. The result was inconclusive but suggestive. There was order hidden inside the apparent randomness, a ratio that repeated almost perfectly 3 times during the 96 seconds. "It's almost like a coded sequence," Navarro said during a conference call, though she quickly clarified that she didn't mean it literally. The phrase stuck anyway, and soon others began using it in their notes. Whether it was physics or coincidence, the resemblance to intentional patterning was impossible to ignore. Still, the team resisted sensational interpretations. The data remained consistent with natural explanations, though none fully satisfied the observed precision. Weeks later, as the analysis continued, an independent team in Germany published a comparative study. They found that the blink pattern shared characteristics with the reflection frequencies of tumbling metallic asteroids. That suggested the possibility that 3I/ATLAS might contain dense metallic inclusions, rather than being composed purely of ice and dust. It was a simple hypothesis, but one with large implications. It would mean the object had undergone processes similar to planetary differentiation, something unexpected for a comet from interstellar space. NASA didn't officially endorse that claim, but they did verify the math. The results were plausible. If correct, it meant 3I/ATLAS wasn't a pristine remnant of an ancient system, but rather a fragment of a larger, evolved body, possibly even a shattered exoplanet. That interpretation reframed the entire story. Instead of being a simple traveller, 3I/ATLAS might be a survivor of destruction, carrying within it traces of a world that no longer existed. In the following months, requests for telescope time surged again. Researchers wanted to confirm whether the blink could be repeated, but the object had already moved beyond optical range. Only deep space radio observation remained viable, and even that was uncertain. Despite the odds, teams submitted proposals, hoping for one more chance to detect something. But the event never repeated. The universe had blinked once and returned to stillness. The last report filed under the 3I/ATLAS program summarized the anomaly with professional restraint. A transient photometric event of undetermined origin duration 96 seconds, non-recurring multiband confirmation. It was clinical and unemotional, as scientific writing demands, but everyone who worked on the case knew it had meant more than the words implied. Something had happened out there, something that reminded them that even when the data ends, the story continues. In the quiet after the analysis, the discussion shifted from what had occurred to what it represented. Science had no shortage of unexplained moments, but this one had come at the edge of observation, just as systems were shutting down, just as the project seemed forgotten. Some called it coincidence, others called it timing. Either way, it was a reminder that discovery doesn't follow human schedules. You imagine standing under the same sky, knowing that for a brief moment, light had reached Earth that may never appear again. It carried information, perhaps meaningless, perhaps profound, and then vanished into space. The scientists couldn't decode it, but that didn't matter. What mattered was that they saw it, measured it, and remembered that the universe, vast and indifferent as it may seem, still finds moments to surprise. The data would sit in archives now, preserved for future review. Maybe one day a new generation with better tools would reopen the files and find something everyone else missed. For now, it remained a mystery wrapped in 96 seconds of brightness, a cosmic blink that bridged silence and meaning, leaving behind the same question that had haunted the team from the beginning. Was it reflection or a farewell? When the shutdown orders came through, most departments within NASA and affiliated observatories were forced to suspend operations. Data streams were paused, communications delayed, and funding pipelines frozen. For the public, it meant another bureaucratic pause in science. But inside the network of astronomers following 3I/ATLAS, silence didn't mean stillness. Many refused to stop their work. They stayed awake, unpaid and unofficial, continuing to track and analyze whatever fragments of data they still had. Among them was Dr. Lena Moravec, a Czech astrophysicist who had been monitoring the object since its first detection. Her personal computer became her observatory. Using offline archives, she processed light curves manually, running calculations with open-source software. Her small apartment in Prague filled with the hum of cooling fans and the soft glow of monitors. She wasn't under contract anymore, but that didn't matter. For her, the pursuit of understanding didn't depend on payroll cycles. Across the Atlantic, a retired engineer named Samuel Richter used his own backyard telescope. His data wasn't precise by professional standards, but he contributed observations to the Minor Planet Center's independent network. He'd been part of NASA's Deep Space Communications team decades earlier, and when he heard about the data blackout, he reconfigured his old receiver equipment. Richter managed to intercept a few weak transmissions before the official systems went offline. Those transmissions contained timestamps that later helped synchronize other data sources. These people, scattered across time zones and continents, became an informal collective. They communicated through encrypted email lists and amateur astronomy forums, keeping discussions quiet to avoid administrative interference. What united them was a shared conviction that information about 3I/ATLAS shouldn't disappear just because funding had stopped. They saw themselves as caretakers of continuity. The challenges they faced were immense. Without access to the central databases, they had to reconstruct observation logs from cached copies. Some used scraped data sets stored on personal drives. Others contacted collaborators in universities outside the United States, where the shutdown's reach was weaker. Piece by piece, they began to rebuild what had been lost. It wasn't official research, it was persistence shaped into method. The group's communication style was practical, almost clinical. They avoided speculation and focused on verification. But beneath the technical exchanges was a deeper emotion, a quiet defiance. Each night, while others slept, they compared exposure frames, checked calibration errors, and looked for consistency in the comet's faint trail. They were driven by a mix of duty and curiosity. When formal science was paused, informal science filled the gap. One night, Lena received a message from another participant, an astronomer in Chile named Rafael Torres. His observatory had remained partially active under private funding. He'd captured a faint streak near the last known coordinates of 3I/ATLAS, possibly a remnant fragment. The data wasn't conclusive, but it reignited the group's determination. They began cross-referencing his images against pre-shutdown trajectories. After 2 days of calculations, they realized the object was moving slightly off the expected course, a deviation consistent with the earlier blink event. That finding didn't prove anything, but it reminded everyone that even unofficial science could still produce insight. They started keeping nightly logs again, writing their notes in shared documents that later formed a digital record of the shutdown era. Those logs weren't stored on NASA's servers. They lived on personal drives, encrypted clouds share, and printed copies mailed across borders. Each entry began with the same phrase, "Observation continues." For these astronomers, continuing was more than a statement. It was resistance to forgetting. Many of them knew their efforts might never be recognized. Without institutional verification, their findings would remain in limbo, unpublished and technically unofficial. Yet the work carried on, driven by the idea that data, once seen, should not vanish into neglect. One challenge they faced was maintaining the calibration standards that kept their data credible. Without synchronized atomic clock signals from NASA's network, even minor timing discrepancies could skew results. To solve this, Richter repurposed an old GPS receiver to generate reference time codes. Others followed his method. The improvised network became stable enough that their observations retained measurable accuracy. What began as a loose collection of enthusiasts slowly evolved into a coordinated, functional research group. During the long weeks of shutdown, they shared not just data but fragments of conversation. They talked about why they chose to keep working, about the satisfaction of tracing something no longer officially acknowledged. One astronomer described it as listening to the silence of space and refusing to hang up. Another said it was about proving that science belongs to persistence, not to policy. Outside their small network, most people had moved on. Public attention had shifted toward other headlines, and 3I/ATLAS became another forgotten story. But within this group, the comet still mattered. They understood that every discovery lives not only in instruments but in the continuity of observation. When the official channels went dark, human curiosity became the only remaining source of light. Eventually, limited government operations resumed, and partial access to research systems was restored. When the main servers came back online, technicians discovered a backlog of independent uploads waiting for verification. Many of those files traced back to the same handful of IP addresses, the astronomers who had refused to stop. The data was tagged, validated, and quietly integrated into the official archive. No one issued formal recognition, but the work was there, now part of the record. In later internal reviews, analysts noticed that some of the most consistent datasets from the shutdown period had come from unregistered contributors. Their precision surprised everyone. When asked how they managed it, one of the group members simply replied, "We never turned the telescopes off." It was a statement both literal and symbolic. By the time operations fully resumed, the team members had already gone back to their regular routines. Some rejoined official research programs, others continued their independent monitoring. None of them sought credit. What mattered was that the data survived and that the story didn't end in silence. In every field of science, there are people who keep watching when others stop, those who believe that discovery is not a career, but a form of endurance. The astronomers who stayed awake proved that even when institutions sleep, curiosity doesn't. They kept the thread unbroken between observation and meaning. As new analyses began again, these quiet nights of persistence became the foundation for the next phase of research. Their efforts would help detect the signal's eventual return, an echo of what they had preserved through sheer determination. The record of their sleepless work now sits in a subfolder of NASA's main database labeled External Corroborations. There are no individual names listed, only timestamps and coordinates, but behind each entry lies a story of people who kept their eyes open when the universe briefly turned away, and who made sure that when the systems woke again, the data was still waiting. And as the world prepared to look for 3I/ATLAS once more, their endurance became the reason the next signal would be recognized at all. When the systems came back online, it wasn't dramatic. There was no flash of light or audible click, just a soft hum returning to the servers as electricity flowed again through the racks. Lines of code reappeared on screens that had been blank for days. For the first time since the shutdown, data packets began moving across the network, slowly at first, then in a steady rhythm, as if the machines were stretching after a long sleep. At first, no one celebrated. The research team had seen false starts before. They had rebooted the network several times, only to find corrupted files or lost data, but this time the signs were different. The recovery log showed that the error counts were low, and the checks and verification was stable. It meant the information being restored was authentic and complete. The astronomers exchanged careful looks, cautious hope replacing the fatigue that had become normal in the lab. The first restored file was small, only a few kilobytes of spectroscopic data from a night weeks before the blackout. When it opened, the numbers matched the final readings taken from 3I/ATLAS before the systems failed. Those values had been a mystery, a strange patterns of fluctuating brightness that didn't fit any known model of cometary reflection. Now, as they scrolled through the graphs, the anomaly made sense. It wasn't noise, it was modulation, a consistent variation that repeated in cycles. Something about the object's rotational surface composition was influencing its light. The next data sets came in larger chunks: infrared imaging, plasma readings, and magnetometer logs. Together they painted a more complete picture of what had happened while the observatory was offline. The comet had not simply vanished from detection, it had undergone a transformation. Its reflective signature had changed, shifting in temperature and wavelength, indicating the sublimation of a different set of compounds. In simpler terms, it had evolved. The surface ice, once crystalline, had begun to vaporize, revealing deeper, more complex layers beneath. The team analyzed these layers with the precision of surgeons. What they found surprised even the most experienced among them. Embedded within the dust and carbon structures were traces of polycyclic aromatic hydrocarbons, the same organic compounds often found in interstellar clouds where stars and planets form. It meant that 3I/ATLAS wasn't just a frozen traveler, it was a messenger carrying ingredients of life through space, and somehow the loss of signal had hidden the very moment it revealed this truth. In the control room, the scientists compared archived data from before the blackout to the recovered streams. They could now see a timeline of change. Before the systems went down, the object had shown a predictable curve in its energy output. Afterward, the curve bent sharply, as though something inside had shifted its reflective properties. It wasn't just a comet fading in sunlight, it was adapting to the deep interstellar environment, as if responding to a new condition of space. Word spread quickly across departments. The communications team drafted reports, while data analysts worked to confirm every decimal. The director of the observatory ordered a full redundancy backup, this time across multiple international data centers. Nobody wanted to risk another disappearance. The reappearance of the signal had reminded them how fragile discovery could be. One power surge, one corrupted file, could erase months of work and a piece of human understanding with it. Late into the night, the lead astronomer stood before the main monitor, watching the signal in real time. It pulsed faintly, steady and deliberate. Each transmission from the telescope arrived as a stream of numbers that represented the reflected sunlight of a comet billions of kilometers away. But those numbers meant more than brightness or motion. They represented resilience, of data, of systems, of curiosity itself. In one of the restored files, there was a fragment of a time-stamped note left by a night shift operator. It simply read, "Still watching. Still here." The note had been logged seconds before the systems failed weeks ago. Now, recovered along with the data, it felt like a quiet message from the past, a reminder that persistence matters as much as precision. As the hours passed, the scientists began piecing together an updated trajectory for 3I/ATLAS. The object's orbit confirmed what they had suspected from the beginning. It would never return. But the data it left behind, especially from the recovered period, was invaluable. It allowed them to reconstruct its composition, origin, and evolution, a complete record of an interstellar traveler that briefly passed through our cosmic neighborhood. When morning came, the lab was still active. There were no cheers or dramatic announcements, just a calm satisfaction filling the room. The hum of the servers was steady again, the lights on the consoles blinking like small stars. The data visualization on the main screen showed 3I/ATLAS in soft shades of orange and blue its tail fading as it moved beyond the solar system. The caption beneath it read, "Signal restored, data integrity verified." For a moment, everyone stopped working and looked at the screen. No one spoke. They didn't need to. The restored signal was not just about recovering lost data. It was about recovering faith in their work, in their ability to reach across the vast emptiness and find meaning in light. The rebirth of the signal wasn't just technical. It was human. It was the quiet proof that even when systems fail and silence takes over, the pursuit of understanding doesn't end. It waits, patient, resilient, for the moment when the universe decides to answer again. By the time the last transmission from 3I/ATLAS was received, the object was already far beyond the range of most instruments. The data came through weak, fragmented, and delayed, arriving several hours after being recorded. It wasn't the dramatic finale some expected, just a gradual fading, a decline in signal strength until nothing remained but background noise. Yet in that fading light, the scientists found closure. The object's journey through the solar system had ended, but its trace remained in the archives, captured across hundreds of terabytes of data and thousands of human hours. At the observatory, the recovery teams finished cataloguing the final data sets. Every spectral reading, thermal image, and positional coordinate was indexed and mirrored across backup systems around the world. It wasn't just an exercise in data storage, it was preservation of history. The mission logs read like a diary of curiosity, each entry marking humanity's attempt to understand something that came from outside its home system. The researchers knew they would likely never observe another interstellar object exactly like it. 3I/ATLAS's path was unrepeatable, its trajectory determined by forces far beyond the influence of any planet or sun. When the trajectory model was finalized, the numbers confirmed what had long been suspected. The comet would never return. It was traveling at more than 30 kilometers per second relative to the sun, fast enough to escape the gravitational pull of the entire solar system forever. Some younger researchers found the realization strangely emotional. They had spent months tracking an object that would vanish from every telescope on Earth. Once gone, it would continue into interstellar space, unseen by anyone, carrying the dust of other stars and the record of human observation on Earth. But not everything was gone. The data was permanent now, stored, shared, and studied. The chemical analysis of its composition revealed new insights into how materials from different star systems could merge and survive long journeys through cosmic radiation. The isotopic ratios in the recovered spectra provided evidence that the object formed in a colder region of space than any comet previously observed. This changed how scientists understood the early conditions of star formation beyond our galaxy. What was once a faint light in a telescope had become a source of new scientific models, a reason to rethink the chemistry of creation itself. NASA's final report on the 3I/ATLAS was cautious but confident. It summarized the mission as a success, not because of dramatic discoveries, but because of the process that unfolded. Every challenge, from the data loss to the eventual recovery, had tested the reliability of the global observation network. The experience led to better coordination between agencies, faster redundancy systems, and new backup protocols for long-term cosmic monitoring. In short, the comet's visit had improved how humanity watched the sky. As the last meeting about 3I/ATLAS concluded, one of the senior scientists reflected on how temporary their connection had been. For a few short months, the object had entered human awareness. It had been observed, measured, and debated, and now it was gone, moving through a region of space so empty that even light took years to cross it. Yet despite that distance, the record of its passage would outlast every observer in that room. The data would remain stored in cold archives, copied across generations of technology, silently testifying to the moment when humans turned their instruments towards something unknown and chose to understand it. In classrooms and research labs, students began studying 3I/ATLAS as a case example of interstellar observation. They used its datasets to simulate chemical reactions, to practice spectral interpretation, and to train machine learning models for future detections. Even if the object itself was gone, it continued to teach. It became a bridge between the practical work of science and the human drive to find meaning in discovery. Over time, the public fascination faded. News headlines moved on, and only specialized journals continued to publish updates about the long-term implications of the comet's data. But in the observatory logs, its name remained pinned to a section marked Interstellar Encounters. It stood beside only a few others, rare visitors from beyond the sun's gravity, each carrying information from regions humanity could not yet reach. One evening, long after the project had been archived, an engineer returned to the control room to perform maintenance on the servers. Out of habit, he opened the visualizer program and loaded the trajectory model. On the screen, 3I/ATLAS appeared as a small blue point moving steadily away from the solar system. The simulation ran in silence. There was no motion blur, no flare of light, just a continuous line extending into the unknown. Watching it, he understood why scientists called space exploration both humbling and infinite. You could measure and record every motion, but you could never repeat it. The future of 3I/ATLAS was simple. It would drift between stars for millions of years, untouched, unseen. Its surface would erode under cosmic radiation, its ices would evaporate, and eventually only a dark fragment of rock might remain. But its story, the data, the numbers, the effort, would persist in human memory. It was the paradox of exploration. Even when the subject disappeared, the act of searching changed those who had looked. When the engineer shut down the visualizer, the lab lights dimmed slightly, leaving only the glow of the server racks. The hum of the cooling fans filled the room. For a moment he imagined that faint sound continuing even after everyone was gone, a quiet echo of curiosity preserved in circuits. The object itself was gone forever, but its record was eternal. Months after the last confirmed signal from 3I/ATLAS, the project had shifted entirely into its archival phase. The observatories that once pointed toward its coordinates now tracked other objects, and the team members who once spent nights monitoring faint readings had moved on to new research. Yet the data from the comet remained a quiet presence in the scientific world, revisited, recalibrated, and reinterpreted as technology improved. It was no longer an active mission, but a reference point, a constant reminder of how brief and fragile interstellar contact could be. In the basement of a data center in California, rows of servers stored the full record of the comet's observation. The system was designed to run automatically, preserving the files through continuous redundancy checks and cloud replication. The files carried tags with timestamps, coordinates, and energy readings. There were terabytes of raw images from different telescopes, optical, infrared, ultraviolet, and thousands of spreadsheet entries containing measurements from across the world. Each one represented a moment when light from 3I/ATLAS touched a sensor on Earth and was converted into data. In a sense, that light still lived here, in the binary code that scientists could open and analyze at will. A graduate student named Lena was assigned to reprocess the infrared data as part of her doctoral research. She wasn't part of the original team, but she admired the story behind it, an object from another star system passing briefly through humanity's reach. When she began reviewing the images, she noticed subtle variations in the thermal readings. Some of the later captures showed patterns that earlier models had overlooked. At first, she assumed it was noise from the sensor array, but the patterns were consistent across multiple instruments. After running several filters and adjustments, she realized they might represent residual emissions, traces of the comet's surface releasing heat differently than expected. Lena compiled her findings into a report and submitted it to her advisor. Weeks later, the analysis confirmed her suspicion. The comet had likely contained complex organic molecules in higher concentrations than previously believed. The discovery didn't suggest life, but it did imply that the building blocks of life might be more common in interstellar material than once thought. The data was reviewed by international research centers, leading to a small but significant publication in a major journal. The findings reignited interest in the 3I/ATLAS, drawing new attention to a mission that many had considered complete. At NASA's archives, a separate team was working on an AI-driven project to reanalyze old datasets using updated pattern recognition algorithms. 3I/ATLAS was included as a test subject. The program processed its data and generated a visualization of the object's entire journey, from its approach to its departure beyond the heliosphere. The animation revealed small anomalies in its motion, possibly linked to non-gravitational forces like outgassing or internal mass redistribution. While these were minor details, they refined the models used to predict the behavior of interstellar bodies. In a quiet way, 3I/ATLAS continued to teach humanity how to see the universe more accurately. Outside the scientific world, the comet still held a symbolic presence. A small museum exhibit titled Visitors Between Stars opened in Arizona, featuring interactive displays about interstellar objects. One section was dedicated entirely to 3I/ATLAS, including a replica of its observed path and the visual simulations of its surface based on spectral data. Visitors could move sliders to change the wavelength of light and see how different parts of the object became visible. Children would point and ask if it might ever come back, and the guides would gently explain that it was gone forever, moving into regions beyond even radio contact. Yet the exhibit's title plaque summed up its meaning simply, "Some lights never return, but their stories stay." Meanwhile, in another part of the world, a group of amateur astronomers organized an online forum dedicated to revisiting old interstellar observations. The forum hosted discussions, shared software tools, and allowed members to download open-source data. 3I/ATLAS remained one of the most downloaded datasets. Some used it for learning, others for testing personal algorithms. In one post, a member wrote, "Even if it's gone, we're still learning from it. That's what makes it immortal." That sentiment echoed through the comments, reminding everyone why the pursuit of knowledge continues even when the object of study no longer exists. Lena's research eventually evolved into a larger project funded by the European Space Agency. The mission proposal, named ECHO, aimed to develop instruments capable of detecting faint heat signatures from deep space objects far earlier than existing systems could. In her presentation, she used data visualizations from 3I/ATLAS to demonstrate the limits of current detection methods and how ECHO could surpass them. The proposal passed its initial review phase, marking a potential next step inspired directly by the lessons of 3I/ATLAS. What began as a comet sighting had quietly influenced the design of future missions. In a broader sense, the legacy of 3I/ATLAS reached beyond astronomy. Data scientists referenced its recovery process in conferences about digital resilience. The challenges of restoring corrupted observation files had led to the creation of better data preservation techniques, methods now applied in medical imaging, climate modeling, and even AI research. The object's journey had indirectly improved how humans handled and safeguarded information. The idea that a fragment of ice and dust from another star could influence human technology years after its departure was not lost on those who studied its impact. Years later, during a public lecture, Lena was asked what she thought the real legacy of 3I/ATLAS was. She paused before answering. "It reminded us that discovery doesn't depend on presence," she said. "Something can vanish physically and still guide us forward. The light we receive, even when it's millions of years old, still changes how we see ourselves." Her words were quoted widely afterward, appearing in articles and science blogs. They captured the sentiment of an entire generation of scientists who had grown up studying data from objects they would never see again. At night, in observatories across the planet, telescopes continued scanning the sky for new interstellar visitors. Each detection attempt carried a trace of what 3I/ATLAS had taught: to preserve, to question, to expect the unexpected. The silence between signals was no longer seen as emptiness, but as a waiting space, the interval before the next discovery. The comet's story had ended, but the process it began was unending, and somewhere beyond all known constellations, the object itself still travelled. It no longer reflected enough of sunlight to be detected, but its path continued, steady, unbroken, and timeless. Its light, captured years ago by human instruments, remained preserved on Earth, stored in drives and mirrored across servers. Though the comet had vanished from sight, the record of its existence endured, proving that the act of observation gives permanence to the fleeting. In the end, 3I/ATLAS became more than a comet. It became evidence of humanity's determination to understand the unreachable. Its light had outlasted its silence, and in that endurance it became eternal.